Hello students, this is your friend Sumit and today we are going to discuss topic 8 of the series, that is moving charges and magnetism. This particular topic is a bit different from the previous topics. Many of the students fear this chapter. They find very difficult to solve questions of this particular topic. But let me tell you, I know what NTA is going to ask in January attempt 2026. So I'm going to tell all the key concepts of this particular topic along with the questions practice. Make sure you don't miss any part of this video, and if you watch the video fully, mention completed in the comment section. Okay, so if you ask what varieties of questions or from which particular subtopic more questions are asked in this particular topic, so I'll say motion of a charged particle in magnetic field and magnetic field due to a current carrying conductor. Okay, so these particular things, two things I'll say are more frequently asked. Other things are also asked. We will discuss those as well. Okay, and with that you need a good amount of practice. For that, don't forget to take DPP and notes, the class notes from the link in the description box. Okay, so when you click that link in the description box, you'll go to our app, join the free batch there, you can access that. And as you know, PW app is one of the most trusted platform where you get quality teaching at affordable prices, so don't miss that opportunity. Okay, so let us begin this discussion. We'll be covering entire chapter, all the details. So major things, first of all, we'll be learning how to find magnetic field due to different types of current carrying conductors, and then motion of a charged particle. We will be discussing about the force due to magnetic field on a charged particle and how it affects the motion of the charged particle. Also the combined, you can say, effect of electric field and magnetic field on a charged particle. So all those things we'll be discussing. Then we'll be talking about the magnetic force on a current carrying wire. Okay, then the magnetic dipole, how to find the torque on the dipole, how to find the potential energy, the work done, all those things. And then moving coil galvanometer. As I already mentioned that these two, magnetic field and the motion of a charged particle, these two topics are majorly asked in JEE mains. Okay, so if you are not understanding few of the things, at least these two things are must to cover. These two things are must to cover, because finding magnetic field is not that much difficult. I'll be explaining everything in a very simplified manner. Okay, so make sure you watch every you can say section of this video, don't miss anything. So first of all, Ampere's right hand grip rule. So it tells, let us take, if a current carrying wire is having a current in this direction, so it tells us about the direction of the magnetic field. So taking our right hand, if we move our fingers, keeping the thumb in the direction of current, we close our fingers like this. So this is how the magnetic field will be. So you'll see that at this point, you see the magnetic field is in this direction. At this point, the magnetic field is in this direction. So this is how we find the magnetic field lines. Okay, this is a straight wire. If let us take, there is a wire of some random shape, so from at that you can find magnetic field due to a small section. Okay, take a small section, see what is the direction of the magnetic field at a particular point. Due to that small section, you can use that right hand thumb rule there itself. Okay, now let us talk about the most, I'll say, appearing difficult topic, that is Biot-Savart law. And Biot-Savart law tells about, let us take, if a current carrying conductor is like this, so it tells us what will be the magnetic field due to a small section of this wire at a particular point P. And if you have to find due to the entire conductor, you can integrate that. Okay, so if I take a small section whose length is dl, current is I, so this becomes my ideal vector. Now due to this dl length at a point P, okay, how we write the magnetic field? We write the magnetic field as dB, and that is mu naught by 4 pi I dl cross R divided by R cube. This is how we write the magnetic field due to a small section. And to find due to the complete wire, you need to integrate it. Now it appears to be very difficult, okay, like how we need to use it, how to integrate and all those things. You do not need to integrate anything. I know what NTA will ask you, okay, those integrations I will do. You have to memorize the result, okay, few of the results, and questions will be asked from them only. So you don't need to integrate by writing this rule. So sometimes what happens, like when you learn Biot Savart law, so many of the students skip, okay, it like seems very difficult for us to learn or like that. So that is not required. Okay, so due to small section, we are able to write the magnetic field here dB, and that is, you can say the direction of dB will be ideal cross R. This is my ideal, this is my R vector. So ideal, right hand thumb rule, ideal cross R. Okay, so it is in the downward direction. So this becomes my dB. What is mu naught? Mu naught is the permeability of the free space. Let me write with different color. This is permeability of free space. Like for electric field, we used to have epsilon naught. That was permittivity of the free space. This is permeability of the free space. Okay, the same thing. You can say like permittivity also tells like how favorable or unfavorable the medium is for the electric field. Okay, so similarly we can say permeability also tells that greater the permeability, greater will be the magnetic field. Okay, so it is more favorable for the magnetic field. Okay, as I gave an example previously that resistivity tells us how favorable the medium is for the current. Okay, greater the resistivity, lesser favorable it is. Lesser the resistivity, greater favorable it is. Okay, so same type of things here. Now mu naught for free space, if I write the value of mu naught by 4 pi, okay, this is 10 to the power minus 7. Remember it like this. If you have to put the value of mu naught at some place, then you can write mu naught as 4 pi into 10 to the power minus 7, and this is in SI units. What is the SI unit of magnetic field? That is Tesla, we know that. Okay, so unit of magnetic field, if I write, okay, that is Tesla. This is our SI unit. And the another is also there, Weber per meter square. Okay, we there for flux we have Weber. Okay, WB, this is how we denote that, and per meter square, that's the same thing. So 1 Tesla is equals to 1 Weber per meter square. Okay, and if you have to, let us take, find the dimensions of mu naught, you can find the dimensions of mu naught from here. Force we will relate with magnetic field. So generally if you have to write, let us take the dimensions of magnetic field, so better way will be to use the one of the formula for magnetic force. Okay, let us take the field is there B, okay, that is perpendicular to the wire, force become BIL, I is the current, okay, F is the force, B, we can find the dimensions of B from there. Okay, L we know that is the length. So using that we can find the dimensions of B, and if we know the dimensions of B, we can find the dimensions of mu naught as well from there. Or another way is, we know that how mu naught and epsilon naught are related with each other with speed of light. So if you know that relation, so that way also you can write, we know V is equals to, the speed of light is equals to 1 by root of mu naught into epsilon naught. Okay, from there also you can relate mu naught and epsilon naught, because why I am discussing this here is, many times mu naught dimensions are asked, like mu naught will be with some other physical quantity, maybe epsilon naught, or maybe some current, or maybe something else like that. Many times mu naught dimensions are asked like that, therefore I am saying. Okay, now let us find magnetic field due to current carrying conducting finite long wire. I am considering a wire whose length is finite. Okay, let us take, let me show it here. Let us take, this is my wire, its length is finite, and we need to find magnetic field due to this wire at a point, okay, that is at a perpendicular distance of, at a point P, and that is at a perpendicular distance of, let us take R. Okay, and the two angles are given to us. Which two angles? This angle, and this. Let us take this angle is okay. Let us take this angle is phi 1, okay, and this angle is phi 2. So these phi 1, phi 2 we know, and this current carrying wire is having a current in this direction like this, and let us take that current is I. Now we need to find the magnetic field at that particular point P. Now I am using Biot-Savart law. Doing the derivation, you need to remember the end result. That's all. Now for you to make you understand how everything is going on, you can see how I am doing. Okay. So let us take a small conductor at a distance L from here. I am taking a small section whose length is dl. Okay, so this becomes my ideal vector there. Due to this ideal vector, I need to find the magnetic field at this point here P. Okay, so this becomes my R vector. Let me make an arrow. So this becomes my R vector. R. If I consider this angle to be theta, how much is the angle between ideal and my R? This angle, how much is this? This is 90 minus theta, this is 90 plus theta. Okay, so this angle is 90 plus theta. Okay, let me write the dB there. So if I write dB, that is mu naught by 4 pi I dl cross R divided by R cube. And what is ideal cross R? If I do ideal cross R, that is inside the plane. And if you find magnetic field due to any of the section, that is inside the plane. It means all the magnetic field due to all the dl vectors, okay, due to all the ideal vectors, the magnetic field is in the direction inside the plane. So I can just sum up all the magnetic field, okay. And if I write the magnitude of this was in vector form. If I write the magnitude for I dl cross R, that will be I dl R into sine of angle between I dl and R, that is 90 plus theta. So this will become I dl into R into sine of 90 plus theta divided by R cube. This is here mu naught by 4 pi. Okay, 1 R will get cancelled. So this is R square there, and sine 90 plus theta is cos theta. So I can write this as mu naught by 4 pi I into cos theta into dl divided by R square, and the direction we know, that is inside the plane. So you may define that as minus k cap, so I can just write that as minus k cap. So this becomes my dB. Now I need to integrate it. I need to simplify it. How to do that? Let me relate dl and my theta. Okay, so in this right angle triangle, which one? Let me take a different color here. Okay, this angle is 90. I'm talking about this right angle triangle here now. This. And this right angle triangle, if I write tan of theta, what it will be? So if I write tan theta there, so tan of theta, that is my perpendicular L divided by the base R. Okay, so L becomes R tan theta. And if I write dl differentiating it, so this will become R secant square theta d theta. Also, if I write this small r here, this distance, small r, what is that? That is capital R by cos theta. Now, let us substitute dl and small r in this equation. So, what it will become? Mu naught by 4 pi, okay, then I, okay, and cos theta, dl was r secant square theta d theta. So r secant square theta d theta, that is clear, okay, divided by r square. What is r? R is r secant theta. So this will become r square secant square theta. Okay, anything else? No, everything is fine now. So this secant square theta is getting cancelled. 1r is getting cancelled here. Okay, and if I simplify it further or write it again here, so this will become mu naught by 4 pi into I cos theta, mu naught by 4 pi r, okay, mu naught I also, mu naught I by 4 pi r into cos theta d theta integration. This becomes my b there. Now let us put the limits carefully. This angle is phi 1, okay, the upper end angle is phi 2. When I am considering my theta, I am taking theta on the positive side, means I am considering theta positive to be on the upper side. So when I have to put limit from phi 1 to phi 2, I need to consider minus phi 1 because I am moving down, okay. So minus phi 1 to plus phi 2. So the limit goes from minus phi 1 to plus phi 2. Now this will become mu naught I by 4 pi r. Cos theta integration is sin theta, so this will become sin phi 2 minus sin minus phi 1, so that will become sin phi 2 plus sin phi 1. Sin phi 2 plus sin phi 1. You need to remember this result. This. Okay, this is important. Now we will discuss different conditions using this result. One condition can be this is a infinite length. Okay, if this length is infinite, my phi 1 and phi 2 both will become 90. If I put 90, 90, this will become 1 plus 1, that is 2 mu naught I by 2 pi r. You remember that formula? Magnetic field due to an infinitely long current carrying wire at a distance r is mu naught I by 2 pi r. Okay, so first condition, infinite length. There we considered both phi 1 and my phi 2 to be 90 degree. So magnetic field B becomes mu naught I divided by 2 pi r. Simple. Clear? Okay. Second is semi-infinite. If it is semi-infinite, semi-infinite means let us take shapes here, okay. Semi-infinite means this is how the current carrying wire is carrying current, and I am finding magnetic field somewhat here, okay, at this point P. So one angle is 0, another angle is 90 degree. This is continued till infinity. One angle is 0, another angle is 90 degree. So what B will become there? Mu naught I by 4 pi r. Put phi 1 as 0, phi 2 as 90 degree. Okay. Now third, let us take a wire is carrying current like this, and I am having a point here P. Now if I ask you what is the magnetic field due to this wire at point P, what that will be? 0. Okay, that is 0, isn't it? So here I will say the magnetic field B is 0. Because one thing is the perpendicular separation. If we talk about what is the perpendicular separation, it is in line. It is in line. If you talk about phi 1 and phi 2, you may say if one is 0, another is also 0, or both may be 180 degree, like that. Okay, so that way also it is 0. So magnetic field due to this wire at a point that is just in front, that is 0. So sometimes what happens, like a diagram is given, find the magnetic field at that particular at a particular point, and the conductor is given to you. So some section is pointing towards that point. If some section is there that is pointing towards that point, magnetic field due to that particular section is 0. Keep that in mind. Fourth case may be some maybe random length, some random conductor somewhat like this here, and magnetic field is asked, let us take at this particular point P. Then what we need to do, then you can draw, you connect both the ends, this end, okay, and then this end. You will get your angles. You need to mention your angle basically with the horizontal, the perpendicular. Okay, this is my perpendicular distance now. So this angle and this angle. So upper one, phi 2 is there. Phi 1, that is in the other side. I considered from down, but that is in the other side. So consider that as negative. Let us take, this is my 30 degree and upper one is, let us take 60 degree total. So when I use the formula here, so I will use mu naught I by 4 pi r sine of phi 2, that is 60, plus sine of phi 1. What is my phi 1? Minus 30, because that is in the upper side, like this. This is how I will be writing that. So some sections, you can say diagrams are given in which some particular section is like this. So this is how we can find. Now there can be a question, find the magnetic field due to a square loop at the center. There you have the 4 conductors. For each conductors, find phi 1, phi 2 and all those things. How to do? Let me show you. Like if a square is there, let us take, okay. And you need to write the magnetic field due to this square at the center. So all the 4 conductors like this direction should be downward. This and this, they are having magnetic field in the same direction, and that is also equal. From symmetricity we can say. So I'll say 4 into magnetic field due to one of the conductor. How to write due to one of the conductor? Mu naught I by 4 pi into the perpendicular separation. That this is the perpendicular separation, that is half of the side. If side is A, that is A by 2 into sine of the angles of the 2 angles. Okay, so which angle? These are my 2 angles now, and both are 45 and 45. If it is square, put it there. So this will become sine 45 plus sine 45. This is 2 sine 45. If there is a triangular conductor like this, then same thing. Okay, let us take at centroid. You need to find the magnetic field. Equilateral triangle is there, and then you find due to one of the conductor, okay, into 3. And for when you are finding due to one of the conductor, find the perpendicular separation, mark the 2 angles, put the values. Only these varieties are there for straight conductor. Next is the magnetic field due to current carrying circular loop. Let us take, we are having a circular loop. It is carrying current I like this, and we need to find the magnetic field at center. So here I am talking about at center, not on the axis. We'll talk about the axis after this. Now how to find this? I'll take one small conductor. Let us take one small section here. Okay, that length is dl. So this becomes my ideal vector. Due to this ideal vector, what is the direction of the magnetic field? That is out of the plane. That is out of the plane. What is the perpendicular? What is my r vector here? This is my r vector. What is the angle between ideal and r? That is 90 degree. Okay. So when I write mu naught by 4 pi, my dB, that is mu naught by 4 pi, and ideal cross r, angle is 90, ideal r sine 90, so that is just ideal r divided by r cube. And what is the direction? This is out of the plane, I am taking that as k cap. Okay, out of the plane I am taking that as k cap. So this will become r square So this will become mu naught by 4 pi into ideal by r square. R is constant, mu naught by 4 pi is constant, current is constant, just integration of dl. dl integration will become the total length, that is 2 pi r. So when I write b, so it will become mu naught by 4 pi into r square, here I, into 2 pi r. This is how we will write this. So pi 2 1 r will get cancelled, mu naught I by 2 pi r. What I consider radius? I consider radius as small r. Okay, so this is 2r, not pi, sorry, pi got cancelled, so that is 2r. Now this formula is very important, make sure you remember it. Mu naught I by 2r. Now you may be asked, what is the magnetic field due to semicircular loop? Semicircular means half of this. Half of this means magnetic field will be half of this. What will be the magnetic field due to quarter of this loop? 1/4. Magnetic field will become 1/4. What will be the magnetic field due to a particular section that is making an angle theta? So just take the proportionality, theta by 2 pi into this. Okay, so if angle is theta, okay, so for an arc making angle theta at center, theta at center, okay, if I write the magnetic field, how I will write this? Theta by 2 pi. So mu naught I by 2r into theta by 2 pi. Just like this. Okay, if theta is 2 pi, that is mu naught I by 2 pi. If theta is pi, half, so it will become mu naught I by 4r. If this is 1/4, this will become mu naught I by 8r, like that. Okay, and direction if you have to check, here what you can do is move your fingers in the direction of the current. Thumb will denote the direction of the magnetic field. Here current is moving in the circle. Move your fingers in the direction of the current. The direction of the thumb denotes the direction of magnetic field. Here that is out of the loop. Okay, and from Biot-Savart law also we can see. So here it is out of the loop like this. Now magnetic field due to magnetic field on axis of a circular current loop. Now we are having a point P on the axis of this loop. Now let us find the magnetic field due to this loop. I am taking a small section here having length dl, okay, this. So this becomes my ideal vector, okay, the very small in this particular direction. Let me show with different color. So this in this direction. So this becomes my ideal vector. Now due to this ideal vector, I need to write magnetic field here, okay. So this is r. If I use the formula for dB, so you will say dB is equals to mu naught by 4 pi ideal cross r divided by r cube. This is how we write. Okay, now this is my r, this is my r, and this is my ideal. Now what is the angle between ideal and r? Now ideal is out of the plane, it is towards z axis, towards positive z axis, okay, out of the plane, and my r is in xy plane. R is in xy plane. What is the angle between the two? 90 degree. Okay, so basically here angle between the two is 90 degree. So if that is 90 degree, so I can write this as mu naught by 4 pi ideal r sine 90. Sine 90 is 1, so it will become ideal r by r square. Ideal r divided by r cube, so r square will remain. 1 r will get cancelled. Now what is the direction of magnetic field? Ideal cross r. The direction of the magnetic field is dB, this perpendicular here. This is the direction of dB. Now if you take another small conductor dl, similarly, okay, it will have its magnetic field dB in which direction? We'll say ideal, okay, ideal is going inside, cross r, ideal cross r, that will be having in this direction, the same amount. So the vertical component will get cancelled, horizontal will add up. So from symmetricity I can see that the resultant magnetic field is going to be in this direction. So what I need to do, just take the horizontal component and integrate. If you want to see whether that the vertical component is cancelling or not, you can integrate that as well. Take the vertical component, integrate it, it will come out to be 0. But directly from symmetricity I can say one small section is here, if I take another small section there, the vertical is getting cancelled, horizontal is adding up. So when I need to find the total magnetic field, I can just take the horizontal component. So if I write dbx, so it will become, if this angle is theta, so this will become db cos theta. And my magnetic field B will be just integration of the horizontal component. Now putting the values here of cos theta, what is variable? R square is variable or constant? No, R square is constant because that will not change. Cos theta is variable or constant? That will remain constant. Okay, if you consider any of the section, that theta will remain the same. Okay, so cos theta is constant, my r square is constant, I is constant, 4 pi mu naught, everything is constant. So putting all the things first, so that will become mu naught I cos theta divided by 4 pi r square. Everything is constant, I am keeping it here. Integration of dl. Integration of dl, that will give us the complete circumference of the loop, that is 2 pi r. Put there 2 pi r. So mu naught I cos theta by 4 pi r square into 2 pi, and I am considering the radius to be capital R, 2 pi r. This will become 2. Okay. Now what is cos theta? This angle is theta, this is 90, this is 90 minus theta, this angle is theta, and this right angle triangle. Okay. So here if I write cos theta, you see this was theta, this is 90 minus theta, so this is my theta, this is my theta. So if I write cos theta, that will be r divided by small r. Put it here, this will become mu naught I r square divided by 2 into r cube. Now what is r? This is my hypotenuse, so this will become root of radius square, that is my perpendicular, and this is my base, x square. So putting it here, so this will become mu naught I r square divided by 2 into r square plus x square to the power 3 by 2. This becomes my B, and this formula is important. Many times questions are asked on this formula in mains, many times. So make sure you remember this formula. Mu naught I r square divided by 2 into r square plus x square whole to the power 3 by 2. You must remember that this x only comes here. X is my variable here. Okay, x only comes here. X changes, the magnetic field will change. Okay, and if you want to find the magnetic field at center, you can put x is equals to 0. So if you put x is equals to 0, what it will become? Mu naught I by 2r, the same formula that we already derived. Mu naught I by 2 pi r, 2r, magnetic field at the center of a current carrying loop. Okay. Now we will discuss questions. There are if you see any question, either there will be a conductor which is having some length, some angles will be given there, or there will be some part that is of circular shape. Not much varieties, only these two things. Let us see some questions. This question was asked in 2024. Let us read it. The magnetic field at center of a wire loop formed by two semicircular wires, radius r1 that is 2 pi meter, radius r2 that is 4 pi meter, carrying current 4 ampere, as per figure given below is alpha into 10 to the power minus 7. The value of alpha is. Let us take the current is like this. Now one is this semicircular, another is this semicircular, and these two are my straight conductors. Now if you see, what is the magnetic field due to this? Zero. I already mentioned that. Where? Here I mentioned. If a point is there that is just in front, like this wire is moving, like or you can say just pointing in the direction of P. Okay, so this P point is just in front, so magnetic field at P is 0. Therefore, due to this it is 0, and due to this also the magnetic field is 0. Now due to this bigger one, what is the magnetic field there? Half of the complete one. So if I say mu naught I by 4R, 4 into R2, what is the direction? Direction is out of the plane, K cap. What is the magnetic field due to this semicircular loop, and what is the direction? So direction will be out of the plane only, and so plus due to this if I write, so that will become mu naught I by 4R1, mu naught I by 4R1, and this is also K cap. So this becomes my total magnetic field there. I need to find the magnitude, so add that, it will become mu naught I by 4, 1 by R1 plus 1 by R2. What is R1 and R2? 2 pi and 4 pi. So 1 by 2 pi plus 1 by 4 pi, that will become 3 by 4 pi. 3 by 4 pi. Perfect? Yeah. Okay. Now mu naught by 4 pi, we know that is 10 to the power minus 7. So mu naught by 4 pi, that is 10 to the power minus 7 into, what is I? The current is, where is I? 4 ampere. Yeah, here it is. So into 4 into 3 divided by 4. So this becomes 3 into 10 to the power minus 7, and everything in SI units, so Tesla. Alpha comes out to be 3. Another question. Now it is having straight conductors. We need to find magnetic field at point O, and this point is just in between here. Okay. The current arrangement is shown. Okay, the magnetic field at point O is. Now due to this section, if I talk about, what will be the magnetic field? 0. Just pointing at O, 0. So remove this. Due to this, the magnetic field at O will be 0. Remove this. Only magnetic field we have due to this conductor and due to this. Both are semi-infinite. What is the formula for semi-infinite? Mu naught I by 4 pi R. How I wrote it? Phi 1 and phi 2, two angles are there. Phi 1 is 0, phi 2 is 90. Okay, so mu naught I by 4 pi R into sine of phi 1 plus sine of phi 2 when I write, so it will become mu naught I by 4 pi R. So magnetic field due to this if I am writing, what is the direction? Out of the plane. Okay, thumb in the direction of current, move the fingers, it is coming out of the plane. Out of the plane means you may take that as J cap. Okay, so it will become mu naught I by 4 pi into R. R is perpendicular distance. How much is that? A by 2. So A by 2 K cap. Fine. Now due to this, what is the direction at O? This is the direction of current. Move your fingers. We'll close it like this. Magnetic field is coming out. Coming out of O means same direction, K cap. What is the formula? Mu naught I by 4 pi. Perpendicular separation is A by 2 only, K cap. Okay. So both are having the same. So this will become mu naught I by pi A. Okay. 2 into that. So mu naught I by pi A, K cap. This becomes my total magnetic field. Just need the magnitude, so mu naught I by pi A. This is how you have to analyze. And these questions are very much asked in mains, very much. I'll show more questions. This is one of the question. Okay. Find the magnetic field at point P. The curved portion is a semicircle connected to two long straight wires. Now these are two long means they are extending till infinity. Extending till infinity like this. I need to find magnetic field at point P. How many sections are there? One is this straight. Okay, another is this straight, another is the my semicircular part. So we will find due to all the three one by one. First of all, due to this section, this is semi-infinite, mu naught I by 4 pi r, direction is thumb in the direction of current, move the fingers like this, so the magnetic field is coming out. I am taking as k cap. So this will become mu naught I by 4 pi r k cap. I got due to this now. Now due to this semicircle, mu naught I by 4r. Complete circle means mu naught I by 2r. Semi means mu naught I by 4r. What is the direction? Move the you can say fingers in the direction of the current. Direction of thumb is the direction of magnetic field. So magnetic field is coming out of the plane, k cap. So plus mu naught I by 4r. Due to this semi-infinite. Now this semi-infinite is along this. Therefore, magnetic field due to this will be 0. I can remove it. Okay, because that is moving along that is this, you can say length is pointing at P. Therefore, magnetic field at P due to this conductor will be 0. So we need to add these. Direction is same, k cap, k cap. So I can write it as mu naught I by 4r. I can take common. So this is 1 by pi plus 1. Mu naught I by 4r, 1 by pi plus 1. Okay, none of the options are matching. So I'm what change should be there? Okay, mu naught I by 2r, 1 plus 2 by pi. Okay, there is some mistake here. All the four options are same. Okay, so the correct answer is this. Mu naught I by 4r, 1 by pi plus 1. There is some typing mistake here. Anyways, leave it. Another question. Find the magnetic field at point P due to a straight segment AB of length 6 cm carrying current of 5 ampere. Now what we need to do here? We need to see the perpendicular distance. We need to see the two angles, this, and just write the formula. Let us take this angle is theta 1, this angle is theta 2, this perpendicular distance is r. So you'll say magnetic field is mu naught I by 4 pi r sine of theta 1 plus sine of theta 2. Just use the formula, no derivation. Now let us find theta 1 and theta 2. This is 5 centimeter, this is 6, this is 5, this is perpendicular. So half is 3 centimeter. If I write sine theta 1, that will become 3 by 5. What is this? 37 degrees. And this is also 37 degrees. Okay, what is the perpendicular distance? This is 5, this is 3. In this right angle triangle, this will be 4 centimeter. Now put the values there. Let us put it. Mu naught I by, what is I? I is 5. So mu naught by 4 pi, I know that is 10 to the power minus n, I'll put it, into 5 divided by r is 4 centimeter. So 4 into 10 to the power minus 2 into sine theta 1, sine 37 plus sine 37, 2 sine 37, sine 37 is 3 by 5, 2 into 3 by 5. 5 got cancelled. Okay, and mu naught by 4 pi is 10 to the power minus 7. So 10 to the power minus 7, and this is 2. So this will become 3 by 2 into 10 to the power minus 7 divided by minus 2, that is minus 5. I hope everything is fine. So this will become 1.5 into 10 to the power minus 5 Tesla. That is option D. Okay. Therefore, I am saying no varieties are there. No varieties are there. Okay. Just use the standard formula. All the questions of this type you can solve very easily. Let us see further. A current of 1.5 ampere is flowing through a triangle of side 9 centimeter each. The magnetic field at centroid of the triangle is. Okay. Let us do that derivation. Okay. Let us make a triangle. let me take this as my triangle. The current is moving. We need to find the magnetic field at centroid, and the current is assume the current is flowing in clockwise direction. Clockwise direction means like this. Now from symmetricity I can say all the three conductors will have same amount of magnetic field at the center and they are in the same direction as well. So I'll find due to one of the conductor multiply with 3 will get the answer. How to do that? Let's see. I'm finding magnetic field due to this. First of all, okay, let me take the bottom one. Easier to analyze. Due to this, I need the perpendicular distance. Which distance? This perpendicular distance. That is my R. I need the two angles phi 1 and phi 2. This and this. I need this angle and this angle. Okay. First of all, let us write this small r. Now we know if I find this total length, how much that will be? That will be L cos of 30, that is L root 3 by 2. Centroid divides this perpendicular in a ratio 2:1. So this will be 1/3 of the total. So into 1 by 3. Into 1 by 3 will be R. So R is equals to L root 3 by 2 into 1 by 3. So what is that? L by 2 root 3. I got it. R as L by 2 root 3. Now let us write the two angles. Total angle, this total angle is 60. This is a bisector. This will be 30. This is 90. So this angle will be 60. And this angle is also 60. Now put the values. Due to one side I am finding formula mu naught I by 4 pi into the perpendicular distance, that is L by 2 root 3. Mu naught I by 4 pi r into sine of 60 plus sine of 60. What is that? 2 sine 60, that is root 3. Okay. But this is due to one conductor. I need due to the complete triangle. So into 3. Into 3. Okay. Now you can solve it. You can put the values. What is I? I is 1.5. Mu naught by 4 pi is 10 to the power minus 7. I is 4.5. 1.5, sorry. And my side of the triangle is 9 centimeter. Convert that to meters. And then you can check which option is correctly matching. Make sure you comment your answer after solving it. Okay. Now when I am discussing these things, now you may be having some, let us take you have some conceptual doubt in any of the point. So what you can do is you can put that in the comments. We'll get back, we'll answer your doubt. Let us read this question. Two identical circular wires of radius 20 centimeter and carrying current root 2 ampere are placed in perpendicular planes as shown. The net magnetic field at the center of the circular wire is. Now net magnetic field I have to find. Due to each one I'll see and then I'll take the resultant. Let us take first the horizontal loop. So due to horizontal loop, the direction of magnetic field will be upward. So magnetic field is in the upward direction. Let us take that as B1. Now due to this loop, the direction of magnetic field will be like I'm moving the fingers in the direction of current, so that is coming out to be in this direction. So this is my B2. And radius is same, current is same, so B1, B2 both will be having same value. Let us take that as B. They are at a right angle, okay? They are at 90 degree to each other. Taking the resultant will be root of b square plus b square, so that will become 2b square, that is root 2b. So the resultant is root 2b. B is magnetic field due to one of them, so it will become root 2 into b is mu naught I by 2r. Now put the values. Pi is 3.14, okay? We have to take, and what is I? I is root 2. Root 2 into root 2 is 2. That will get cancelled with this. What is R? R is 20 centimeter. 20 centimeter means 1 by 5. So this is 5 mu naught basically. Fine. Yeah. Okay. Now put the value of mu naught, that is 4 pi into 10 to the power minus 7. So 5 into 4 pi into 10 to the power minus 7. This will become 20 pi into 10 to the power minus 7, or I can say 2 pi into 10 to the power minus 6. So that is 3.14 into 2, 6.28 into 10 to the power minus 6. 6.28 into 10 to the power minus 6. I did some mistake. No, here this is 10 to the power minus 8. So that will become 628 into 10 to the power minus 8. This much is the resultant. Okay. Nothing complicated. Same things are there. So how can there be any, you can say, varieties? Only two things are asked: magnetic field due to a loop and magnetic field due to a straight conductor. That's all. Now this is another question. We are having a current loop having two circular arcs, okay, joined by two radial lines as shown in the figure. The current, it carries the current 10 ampere, the magnetic field at point O. Now I need to find magnetic field at O. How many conductors are there? 1, this, and this is in the direction of that point O. Magnetic field due to this will be 0. So it will not contribute to the magnetic field. Similarly, this will also will not contribute to the magnetic field. Only the magnetic field will be due to this and due to this. Now, if you see the direction, see the direction carefully always. If you see the direction, the magnetic field due to upper one is out of the plane and due to lower one is into the plane. Okay, so they will subtract. So when I write here magnetic field, also here this angle is 45 degree. So when I write the magnetic field due to one of the sections, so mu naught I by 2r into theta by 2 pi. Theta is pi by 4 divided by 2 pi. Fine. Okay. What it is now? So that is mu naught I by 4 into 2, 8 into 2 is 16r. Mu naught I by 16r. Now they are in the opposite directions. Due to upper one it is out of the plane, due to lower one it is into the plane. So upper one is having lesser radius, so more due to that. So the resultant will come out of the plane only. Now if I write it, the net magnetic field, so this will become mu naught I by 16 into 1 by r1 minus 1 by r2. Got it? Why I wrote minus? Because they are in the opposite directions. When you write B due to this, B due to this, one will come out to be in k cap, another will come out to be in minus k cap, so negative sign will be there. Now put the values of R1, R2, put the values of value of current. What is current there? Current is 10 ampere, okay, and put the value of mu naught, then you can solve it. Make sure you mention your answer in the comments. So I am seeing how many of you are solving these questions with me parallelly. Now, the important thing to understand is, in mains, nothing complicated is asked. There is not a single thing that is very complicated and that is asked in mains. Always, if you see, always, simplest of the things will be asked. But the point is, we miss the easy things. We miss the easy thing. You see this question, sir, what is this? We can do it very easily. You will not solve this. You will waste your time with many of the things which are not asked in mains, and then when you sit in the mains paper, you see these type of things and you try to solve, you didn't practice, you will not be able to solve. Okay, you should have some practice. Okay, so if you practice these type of things, for sure you will be able to solve in the exam. Now let us discuss about Ampere's Circuital law. So Ampere's Circuital law says that, let us take, there are current carrying conductors like this. This is I1, this is I2, this is I3, this is I4. Now I am drawing making a Amperian loop, hypothetical loop, okay? I'm moving in this path like this. And what I'm finding integration of B dot dl in this loop. I'm finding integration of B dot dl in this loop. And when I'm finding that, this comes out to be mu naught into I enclosed by this. I enclosed by this loop. What is the current that is enclosed by this loop? And we have to take that also with proper signs. So my loop is going like this. Whatever is the current in the upward direction, I'll take that as positive, and in the downward direction, I'll take that as negative. So I2 plus I4 minus I3. Okay, this is Ampere circuital law. I1, if you see, I1 is out of the Amperian loop. If I1 is out of the Amperian loop, I1 will not contribute to integration of B dot dl. Okay, so just write it like this, and this loop is completed. Okay, it is coming from the back side like this. This we say this is my Amperian loop. Now this helps us to find magnetic field due to certain type of current carrying conductors if symmetricity is there. Okay, the same way as we used Gauss law. We used Gauss law to find the magnetic field. Okay, we used Gauss law to find the magnetic field, to find the electric field for the cases where symmetricity was there. Similarly, we can use Ampere circuital law to find the magnetic field where symmetricity is there. Okay, I'll show you. Now here we are having a long uniform wire. I already discussed what is the magnetic field due to a long uniform current carrying wire. This is my long uniform current carrying wire, carrying a current I in this direction. I'm having a point P at a perpendicular distance. Let us take this as my R, and if I ask you what is the magnetic field at P, you will say both the angles are at 90 degree, mu naught I by 4 pi R into sine 90 plus sine 90, it will become mu naught I by 2 pi R. You know that formula, we already did that. But now here what I will do is I'll make a Amperian loop like this from symmetricity. This is a circular loop I am taking. Okay, now Amperian loop need not be circular always. It can be any random shape. Ampere circuital law will be valid. If you take any random shape, integration of integration of B dot dl in that particular, you can say, sense will be equal to this, any random shape. But here I am taking a circular loop so that the magnetic field at all the points will be same. Okay, these points are at the same distance from this loop. The magnetic field at all the points is B. So if I write integration of B dot dl for this case, this is my mu naught into I enclosed. I enclosed is the current of this conductor I. So integration of B dot dl, B is everywhere same, and B is in the direction of my dl vector in this. So B dot dl will just become B dl. Okay, B dot dl will just become B dl, and when I integrate, B is constant, taking that out, integration of dl will become 2 pi r, so it will just become B into 2 pi r. And also one more thing, we used to write it like this in a closed loop. In a closed loop. Okay, integrating in a closed loop. So B into 2 pi r is equals to mu naught into I enclosed, and I got the formula for magnetic field directly, mu naught I by 2 pi r. If symmetricity is there, we can find by using Ampere circuital law. Now, let us find magnetic field due to a solid current carrying cylinder, or you can say cylindrical wire. Okay, let us write that. Magnetic field due to cylindrical, this is a long, okay, let me write that. long uniform cylindrical wire. Let us take a cylindrical wire is there. Okay, it is carrying current along the axis, okay, like this, I. Let us take the current is I, and we need to find the magnetic field. This is long, okay, it is continuing like this from minus infinity to plus infinity. Let me draw the axis of this cylindrical wire. This is the axis, and let us take the radius here is my r. So two cases can be there. First case, the magnetic field inside the wire. Second case, magnetic field outside the wire. Let us take both of them one by one. First of all, if I talk about magnetic field outside the wire, that is very easy to write. Here my r greater than r. Okay, so I am having a point at a distance r which is greater than r. I need to find magnetic field there. So what you will do, you will draw an Amperian loop, and from symmetricity I will draw it like circular loop like this. On this circular loop, if I integrate B dot dl, that will become mu naught into I enclosed is I. Integration of B dot dl will come out to be B into 2 pi r. Mu naught into I enclosed, B is just mu naught I by 2 pi r. This case is clear for us. This is very straightforward, very easy. Now the point is how to find magnetic field inside. Second case, that is inside. Inside means at r less than r. Okay. So let us take a point is there where somewhat here. Let us take this is my point, and this is at a distance r like this. Now what I will do, I will use Amperian, draw the Amperian loop like this of radius r, small r. In this Amperian loop, if I write, I will say integration of B dot dl, and this is equals to mu naught into I enclosed. Now here the enclosed current is not equal to the current of the total conductor, because my enclosing loop is inside that conductor. So current will be less than the total current. How much? Here I am saying, considering this is a uniform condition, means the current is uniformly distributed in the cross section. The current is uniformly distributed in the cross section. This is a solid current carrying conductor. From area pi r square, total current I is passing. How much current will pass through area pi small r square? You will say, if I want to write that, I will say the current per unit area will be the current divided by total area. This is my current per unit area into the area of the loop pi r square. Pi got cancelled. I got I enclosed as I small r square by capital R square. Got? Write it. B dot dl integration will be just become B into 2 pi r. This is equals to mu naught into I enclosed I r square divided by r square. Here one small r will get cancelled, and I can write B as mu naught I by 2 pi r square into small r. Here you see magnetic field is directly proportional to small r. Everything else is constant, directly proportional to square r, small r. As I am moving outside, okay, means as I am moving away from the axis inside the conductor, the magnetic field is proportional to r. When I am moving outside, the magnetic field is inversely proportional to r. If somebody asks you, draw the curve, okay, how it varies, how the magnetic field is varying with the distance from the axis. then we can draw. Let us take this is R, this is B, this here is my R equals to the radius. So till R is equals to R, the magnetic field is increasing linearly, means like a straight line like this. After that, it is going like this. Okay. This is mu naught I by 2 pi into R on the surface, the maximum magnetic field. What if this is a hollow cylindrical conductor? Let us take the conductor is hollow. So inside magnetic field will be 0. Enclosed will come here 0. Outside magnetic field expression will remain the same. Okay. So this was my solid cylindrical. Okay. You can write it here. Solid. If I talk about hollow, let us write that for hollow. So what you will say? For outside case, R greater than R, magnetic field will remain the same. Okay. For inside case, R less than R, if I talk about, I enclosed is 0. So the magnetic field is 0. Okay. And there if you plot the relation, let me take different colors. So how it will go? So first it will be 0, then it will become mu naught I by 2 pi R, and it will go like this, 1 by R relation further. This is my R is equals to R, and this is mu naught I by 2 pi R. Simple. Nothing complicated. Okay. Now next maybe sometimes questions are from coaxial current carrying wires. Okay, coaxial means there what happens, like the inner part, let us take is taking current outside, or you can say in the upward direction. So the outer part is having the same current in the downward direction. So that we say that as a coaxial conductor. So if I say coaxial conductor, there the inner part, I am drawing the inner one, okay, and the outer one. Like this. So inner one means here the current is distributed in this is solid one. In between you can say free space is there, or some insulating material will be there, okay, and rest of the current will be moving from the, you can say this is a hollow cylindrical type of conductor there. Okay, so here if I say my current I is going in this direction like this, so that is flowing through the cross section, and from this the current I will be going in the opposite direction like this. Now here if I ask you what is the magnetic field, outside total current is 0, I is going up, I is going down, total current is 0. In between magnetic field be non-zero, okay. Inside this magnetic field be non-zero, okay. So inside this you can again use that relation to find the area from that particular cross section, mu naught I R, sorry, that is pi into R square divided by capital R square into the total current. So let me write all the three cases. So if I talk about outside case, R, let us take that as my greater than R. What is R? Capital R I am taking to be the outer radius. Let me take this as B, not capital R. Let us take that as B. So this is my B, R greater than B. So somewhat here a point is there. You will draw an Amperian loop like this. What is the enclosed current? Total current is 0. Plus I minus I. Total current is 0. So here I will say magnetic field comes out to be 0. If I talk about in between, in between means my R is greater than A, less than B. Okay, so my point is somewhat here. So this is how I will draw my Amperian loop, and there the current, enclosed current, becomes equal to I, and there I will say that the magnetic field B will become mu naught I by 2 pi R. I have mentioned capital I there. Okay, so you can make it capital I. Okay, now if I talk about the you can say inside the inner conductor, the third case, inside the inner conductor. Okay, what is that? R is less than A. R is less than A, then again you will write B into, what is, first of all let us show the Amperian loop. So the Amperian loop, the point is somewhat here, the Amperian loop is like this. Okay, so that will become B into 2 pi R is equal to mu naught into I enclosed. So B into 2 pi R is equals to mu naught into, what is I enclosed? I enclosed will become the current per unit area into the area there. Don't remember these things, understand the concept. Okay, don't make like, you know, this formula for this formula for this formula for this, then you will get confused. Just try to build the concept, how we have to draw the Amperian loop, how we need to write the magnetic field there. Okay, now we are talking about solenoid. Now solenoid, as you know, this is a helical shape. Okay, it is going like this. The radius is uniform throughout. Here the distance between each of the loop, that is also constant, that is not changing. So this is, we say this shape as the solenoid. Here we consider, let us take the current as going like this, I. The current I will be coming out like this. Now what I am doing is, I need to find magnetic field due to a solenoid. First case inside the solenoid, second case outside the solenoid. Now here we are making some assumption, and that assumption is that this solenoid is a long solenoid. This solenoid is a long solenoid. Long solenoid means the radius of this solenoid is very small as compared to the length of the solenoid. If I say the length is L, the radius here to be R, so this assumption means my L is greater than R. And if that particular condition is there, the magnetic field inside the solenoid is uniform. If this particular condition happens, if the solenoid is long, the magnetic field inside the solenoid is uniform, because if you take any point inside the solenoid, okay, if you take any point inside the solenoid is very long. Okay, each point is, you can say symmetrical to the another one. Okay, so therefore we say magnetic field inside is uniform. Now, and the magnetic field outside is 0. Here the magnetic field is uniform inside. This happens only for the condition where the solenoid is long. not for the short solenoid. Now let us find what is the magnetic field. So if I make an Amperian loop, how? Let us take, I am making a Amperian loop like this. Okay, it is going inside, coming like this. Now let me show you in a different way. Dot means coming outside. Here the current is coming out, and down here cross the current is going inside. Okay, so what is this? I cut this solenoid in two parts. I am just showing you the view, front view then. Okay, so here the conductors are coming like this, going inside like this. So the current is here coming outside and then going inside like this. And my Amperian loop is my this. Okay. Now, if I talk about outside, the magnetic field is 0. Outside the magnetic field is 0. Inside the magnetic field is uniform, and here we consider to be B, and we can see that B is towards the right. If the current is going like this, yeah, here the magnetic field is uniform and that is towards the right like this. This is how the magnetic field is there. Okay, now this I need to find B dot dl for this loop. Let us take this as A, this is B, this is my, okay, let me take a different color. This is A, this is B, this is C, this is D. So when I am writing integration of B dot dl, so I can write integration of B dot dl from A to B for AB, A to B, okay, then B dot dl from B to C, let me write it like this, then integration of B dot dl from C to D plus integration of B dot dl from D to A, and this is equals to my mu naught into I enclosed. How many current, how much total current is crossing through the loop, or how much current is enclosed by this loop. Now I am considering here current to be I, okay, so I, this I, this I, this I, this I, and there may be more also, okay, just I showed it like this, there can be more also. So how, basically it will be I into the number of conductors that will come into this much length. Let us take this length to be L, not that L, I already used that for, okay, let us take this this particular length to be some variable, what, let us take that as D, let us take this as my D, okay. So I will say total current will be mu naught into the current of one conductor into number of conductors, into number of conductors. How many number of conductors are crossing? Here we define number of turns per unit length. So if the number of turns per unit length is small n, this is number of turns per unit length. If the number of turns per unit length is small n, so how many conductors will pass through this loop? How many? N into D. Because total turns, it is the number of turns only, okay, that is the number of conductors here. So how many turns? N into D. So this will become I into N into D. Okay, now from A to B, if I talk about magnetic field, if you talk about the portion of the loop that is outside, there B is 0. If you talk about the portion of the loop that is inside, your dl is in this direction, your magnetic field is towards the right, the, you can say dot product will be 0 because they are at 90 degree, so this is 0. If you talk about B to C, magnetic field is uniform B, and this is the direction of your dl only, so it will become B into this length, that is B into D, plus For C to D, same logic. For this, it will come out to be 0. So this is 0. For A and D to A, for D to A, the magnetic field is 0. Outside it is, magnetic field is 0. So this is also 0. So it just became B into D. So plus 0 plus 0. Okay. So B into D is what? Mu naught into I enclosed like this. D got cancelled. So from here, my magnetic field comes out to be mu naught into Ni. This is the simplest explanation to find the magnetic field due to solenoid. There is another method also that is way longer. Like you take each of the you can say loop, and due to that particular loop you find the magnetic field there, and then you integrate it. Okay, so using that you can find even magnetic field due to short solenoid also. Okay, but that is not required for mains. Don't go for that. Just remember this formula. Due to solenoid, magnetic field is B, that is mu naught into Ni. Here N is not the number of turns. N is number of turns per unit length. In the questions, length will be given, number of turns will be given. You need to find number of turns per unit length. Make sure you remember it, this point, okay? And I is the current in the solenoid. Okay, and sometimes we write this as mu naught into H. H we define as magnetic intensity. Okay, that is my Ni basically. What is this H? This is H is Ni, and this we call as the magnetic intensity. Okay, now we are talking about toroid. So as you can see, solenoid is there. What you can do is turn the solenoid in a circular shape and connect the two ends. It becomes a toroid now. So first in solenoid these two ends were straight, and I turned that into a circular shape, connected like this. So the current is coming here and going here. Getting it? Now all the three conditions: magnetic field at a distance small r, that is less than the inner radius; magnetic field at a distance small r, that is in between the regions, okay, and the third one is outside the region. So let us take that one by one. So first case, my magnetic field at a distance r, that is less than the inner radius. Less than the inner radius means I am taking a point somewhat here. Let us take, this is my Amperian loop. If that is my Amperian loop, so how much is the current enclosed by the Amperian loop? 0. So here I'll say that B comes out to be 0. Okay. Next condition, in between means R is between A and B. Okay. So R is greater than A, less than B. And here, let us say this is the point where I need to find the magnetic field. This becomes my Amperian loop. Okay. This for this Amperian loop, if I write B, integration of B dot dl in the closed loop, this is equals to mu naught into the current enclosed. How much is the total current that is enclosed by this loop? So I will say here, let us take total number of turns n into the current in each turn is I. Okay, so total number of turns into the current I. Here n I am considering as total number of turns. Getting? So this will become B into 2 pi r, and this is equals to mu naught into Ni. So B comes out to be mu naught n by 2 pi r into I. Okay, so this is how we are able to write it. And let us take this this you can say thickness of the solenoid is very small. There is not much difference between A and B. So n by 2 pi r we can just write as number of turns per unit length. Okay, so this comes out to be mu naught into Ni, the same formula for solenoid, and this becomes turns per unit length. Clear? Now the third case, that is R greater than B, this was let me use another color. This was the case we discussed. This was the first case, and now the third case, that is R greater than B. R greater than B means you are taking your point somewhat outside here, and this becomes your Amperian loop. How much is the current enclosed by the Amperian loop? 0. If that is 0, magnetic field B will come out to be 0. The same logic for the solenoid, magnetic field outside the solenoid is 0. Is this clear? Okay. Now the questions part. First of all, we are having a question in a coaxial straight cable. We already discussed about the coaxial cable. Okay, the central conductor and the outer conductor carry equal current in opposite direction. Yes, the magnetic field is 0. Where the magnetic field is 0, we discussed that. So say this. Take a pause in this video. Okay, see the options. Make sure you comment your answer, and then you can resume this video. I hope you are back. Okay, so we discussed that if you make a loop outside the cable, how much will be the current enclosed? 0. I plus I minus I, total will be 0. So that is 0. If you talk about in between, inner current will be there, so it will not be 0. If you talk about inside the outer conductor, so that is also not 0. Okay, current will be enclosed due to the inner one. Inside the inner conductor, that is also not 0. Okay, so outside the cable, see, the total current enclosed will come out to be 0, so the magnetic field will be 0. Next question, the magnetic intensity at the center of a long current carrying solenoid is found to be this. If the number of turns is 8 per centimeter, the current flowing through the solenoid is. Now here this is magnetic intensity, and you see the unit, this is ampere per meter. This is basically H, that was Ni. N into I, N was number of turns per unit length. So per meter comes from here, and I, ampere. So ampere per meter, it means this is H. So H is basically N into I. What is H? 1.6 into 10 to the power 3. What is N? Number of turns per unit length. Turns, okay, if the number of turns per centimeter is 8 per centimeter, I need to convert into per meter, because SI units only I will put the values. Okay, so per meter how much? 100. 8 per centimeter. Okay, so per meter will become 800 into 100. Okay, so 800. So this N is 800 into I. What I need to find? I need to find the I. So I will become 1600 divided by 800, and this comes out to be 2 ampere. Very easy questions are asked in mains. These are all PYQs. These are previous year questions, and you can see the level of these questions. How much time we are spending to solve question. See another question. A long straight wire of radius A carries okay, this is a long straight wire of radius A carries a steady current I. The current is uniformly distributed, okay, across its cross section. The ratio of magnetic field at a distance A by 2 and 2A from the axis is. So it's the same thing I discussed. Okay, it's a long cylindrical wire. We need to find the magnetic field inside and outside. You know the formula we just did, but don't remember the formula. Resolve it. Okay, so this is my wire. Okay, radius is A. Let us take for outside. I need to find magnetic field at this point, that is at a distance of 2A. So if I write B into 2 pi into R is 2A, this is equals to mu naught into I, enclosed will be I itself. So what is B there? So mu naught I by 4 pi a. Okay. Another case at a distance a by 2. Now a by 2, so my Amperian loop will be somewhat like this, of radius a by 2. How much will be the enclosed current? We'll see. So B into 2 pi into a by 2, this is equals to mu naught into I enclosed is current per unit area into area of the loop pi a by 2 square. Fine. Okay. 1 a by 2 pi, anything else, 1 a here, so it will become mu naught I by 4 pi a. So B will become mu naught into I by 4 pi a. So you see, this is also mu naught I by 4 pi, this is also mu naught I by 4 pi, so this is 1:1. C option is there. I didn't use formula here so that you understand that you don't need to remember that. Magnetic force on a moving charge. Let us take a charged particle having charge Q, moving with velocity v in a certain direction, and their magnetic field is B. So if we write the force due to magnetic field on this charged particle, that force is Q V cross B. Remember it, Q V cross B. This is how we find the force. If you have to write the acceleration, so we will say acceleration is Q V cross B. This is my force divided by mass. When this magnetic field will be magnetic force will be 0 on a charged particle, when it can be? First case Q is 0, it can be 0. Another case B is 0, it can be 0. Another case V is parallel to B. If a charged particle is having a velocity in the direction of the magnetic field, the force due to magnetic field on that charged particle will be 0. Okay. So F is 0 when three things I mentioned: V is 0, or B is 0, or V is parallel to B. Both are in the same direction. So V cross B will become 0 because magnetism is QVB sine theta. Sine 0 is 0. So this will become 0 then. Both are parallel. Keep this thing in mind. This is important. Okay. Now, Lorentz force. Here we will talk about the combined force due to magnetic field and electric field on a charged particle. So if I say magnetic field, that is Q V cross B. If I talk about electric field, you will say that is Q into E. Okay. So if I say total field, total force, so what that will be? That will be the sum of the two forces, vector resultant. Okay. So that we say as the Lorentz force. Also, in this particular case, when I was saying that force is equal to Q V cross B, you are able to understand that magnetic force will be present when the charged particle is moving. If the charged particle is at rest, magnetic force will be 0. But electric force, that is electric field into the charge, if the charge is at rest, the force will be there. If the charge is at motion, the force will be there. Okay. And one more thing, if the charge become opposite, means the polarity of the charge is opposite. Charge is plus, the direction will be V cross B. If the charge is minus, the direction will be opposite of the V cross B. Negative sign will be considered there. You understand that, I hope. So let us write that. So let us take E is my electric field, and B is the magnetic field. Charges Q having some velocity V, the mass of the charge is M. Now here if we write the two things, so total force will be the vector resultant of the electrostatic force or I'll say the force due to electric field plus the force due to the magnetic field. Let me write that as this as capital E, this as capital B. What is electric force? Charge into the electric field. What is due to magnetic field? Q into V cross B. Okay, and if you you can take common Q from here, you can say this will come out to be E plus Q, anyways Q is outside, V cross B. So basically you can see individually what is the force due to electric field, what is the force due to magnetic field, and you can see how the particle will move. Total force is in this direction, so the particle will move like this. This is how we can say. Okay. And can these two forces cancel each other? Yes, that is possible. We'll talk about that. Now, motion in a magnetic field. Let us take a charged particle enters a region of magnetic field, and we'll talk about different conditions when it enters with a velocity that is perpendicular to the magnetic field, and second case when it is having some angle with particular magnetic field that is there. Okay, so case 1 I am saying where the velocity is perpendicular to the magnetic field. Let us say the magnetic field is inside the plane. Inside the plane we denote with cross. Outside the plane we denote with dot. So here the magnetic field is uniform everywhere, okay, and that is inside the plane. Magnetic field is B. This is uniform. My charged particle is, let us take here, having velocity V. Charge is Q. So if you talk about the direction Q, V cross B, the force is in the upward direction. Okay, force is in the upward direction at this instant, and then it will move like this. Okay, then the force will in this direction. So overall if you see, the direction of force is always perpendicular to the velocity. Direction of force is always perpendicular to the velocity, and the particle is moving in the plane, so it will move in a circle like this. At any point if you talk about, the direction of force is towards the center. It will move with a constant speed. It will move with a constant speed. Okay. And here the magnetic field is not changing with time, and magnetic force is always perpendicular. If that is not changing with time, it means the magnetic force when we are talking about, that is Q V cross B, always perpendicular to the velocity. It means the work done by the magnetic field will be zero always. If the work done will be zero, the magnetic field cannot change the speed. It means it cannot change the kinetic energy of the particle. Isn't it interesting? If the magnetic force, or again let me repeat it, if the magnetic field is not changing with time, okay, then what is happening? There will not be any induced electric field. We will talk about that later on. So therefore I am saying if the magnetic field is not changing with time, the work done by the magnetic field on the charged particle will always be zero, because that force is always perpendicular to the velocity. If that force is perpendicular to the velocity, work done by that will always be zero, because displacement is always in a perpendicular direction to the force. Work done will always be zero. It means the magnetic field cannot change the kinetic energy. The particle will always move with the same speed. Keep this in mind. This is an important point. Okay, and here this is moving in a circle. Can you find the radius of this circle? Yes. How much is the force? This magnetic force, the magnitude is BVQ, because perpendicular anyways, BVQ sine theta. So Q BV sine theta, theta is 90 degrees, sine theta is 1, sine 91. Okay, so this force is equal to mass into centripetal acceleration. Mass into centripetal acceleration is V square by R. So from here I can say that V will get cancelled. Okay, V will get cancelled. My radius, I can find here what is radius R, that comes out to be mv by bq. This is the radius of this circle. And how much is the time period of this circle? So time period is the total path length. It is moving with same speed. Okay, this is the total path length, that is the circumference, and divided by the velocity v, the speed v. Now you can put it r here. So this is 2 pi by v into mv by bq. What it is, v got cancelled, so this is 2 pi m by bq. This is my time period. And what is omega? Omega is 2 pi by time period. Omega is bq by m. Don't remember everything, just remember this thing. Just remember omega. What is time period? 2 pi by omega. 2 pi divided by bq by m. What is radius? Radius is v by omega, because v is equals to r omega, na? So radius is equals to v by omega. V divided by omega, bq by m. So just remember omega. You can remember the three results. Just keep this one thing in mind. Omega is equals to bq by m. That's all. Don't remember anything, because many times what happens, students try to remember each and everything and then they miss. Sometimes they take mass in the numerator, sometimes they take mass in the denominator and get confused. So just remember omega. Omega is bq by m, and by using omega I can write r and I can write t as well. Okay. Next condition, when the magnetic field is at a particular angle with the velocity. Let us take some particular angle, theta is there. Okay, so second condition, let me write case 2. Okay, case 2 with this color only. So when angle between velocity is not perpendicular to magnetic field and neither the angle is 0. Okay, so when angle between velocity and magnetic field is theta, okay, which is not equal to 0 or 90 degree. That is the condition. Let us take the magnetic field is uniform like this. This is my magnetic field. This is uniform, okay, and my charge particle at some instant is here, having some velocity v in this direction, charge is q, mass is m, and it is at an angle theta with the magnetic field. Now what I can do is I can take the component of the velocity in the direction of the magnetic field and perpendicular to the magnetic field. Due to the component that is in the direction of magnetic field, if you talk about, if let us take velocity is in the direction of magnetic field, the particle will just keep on moving like this. If you talk about the velocity that is perpendicular to the magnetic field, the particle will keep on moving in a circular motion like this. Circular motion like this. Now one component is making this move in the circle, another component is making it move along the direction of magnetic field with uniform velocity, means uniform speed, same thing. Okay, that direction will, because the horizontal component is there along the magnetic field, okay, that will not change, that will be constant, moving like this. The vertical component, that will keep on changing the direction, moving in a circle. So if you see the combined effect, how the particle will move, it will move like this, moving like this, moving in the circle also, at the same time moving in direction of magnetic field also. And what is that motion? That is helix, or we say helical shape. How it will move? It will move, let me show the two components first. So the parallel component, v cos theta, it's not proper, let me write it clearly, v cos theta, and the perpendicular component, this is v sin theta. Okay, and how my charge particle will move? The charge particle will move like helical motion. And if you see the pitch means the separation between the two loops, okay, that is constant. because the horizontal velocity is also constant, therefore that pitch is constant. Okay, now let me write different things here. First of all, time period. What was the time period in circular motion? 2 pi m by bq. Was that dependent on velocity v? No, that was independent. So time period will remain the same. So time period 2 pi m by bq. Okay, and I can say my omega bq by m, that remains the same. Second thing, if you talk about the radius, what is radius? Radius is v by omega, and which velocity I need to take? The perpendicular velocity. The perpendicular velocity. So v perpendicular divided by omega bq by m. What is v perpendicular? V sine theta. So v sine theta, or I'll say mv sine theta here, mv sine theta divided by bq. That is my radius. Third thing, pitch. We denote that with p. How much is this? Pitch means this separation between the two consecutive loops. So how much horizontal or how much distance in the direction of magnetic field it traveled in one time period? That is the meaning. That velocity is constant. What is that? V cos theta. So this is just time period into V cos theta. This pitch concept is important. Questions are asked from this. Okay. So time period, what is that? 2 pi m by bq into my velocity component, that is V cos theta. So into V cos theta. Okay. So you are able to understand. This is a motion is helix, or we call it helical path, and it is the pitch is uniform here. The pitch is not changing. Can the pitch change? Is it possible to change the pitch? Yes, that is possible. How that is possible? If I apply a horizontal electric field, let us say I apply electric field in the horizontal direction, then what will happen? The velocity in the direction will keep on increasing. Okay, so the pitch will keep on increasing. It will keep on, the pitch will keep on increasing like this as it will move in the direction of field. That's it. If the charge is positive. Charge is negative, it will move in the, you will say the pitch will keep on decreasing in that particular case. That's all. You got it? Another case can be when angle is 0. You can write that as well. Case 3. You not write that, but let me write it also. So when theta is 0 degree, it means this is the magnetic field and this is my velocity. How the particle will move? Keep on moving in the same direction. Because the force is 0, it will keep on moving in a straight line with constant speed v. Now let us come to the questions. So first question, magnetic field is given, the speed is given, we need to find the force on the electron. How to find that? Q v cross b. Now you need to learn how to take the cross product. I cap, j cap, k cap, the velocity is given in terms, the component of the velocities are given. Similarly, the magnetic field is given in terms of I cap, j cap, k cap. Then you need to learn how to find the cross product of that. You know that, or should I tell you? Like if let us take velocity is vx I cap, vy j cap, vz k cap, magnetic field is bx I cap, by j cap, bz k cap. If you have to take cross product, q v cross b, basically I need to find v cross b. Then how we take? We will draw a matrix I j k. This is v cross b. First write v, vx, vy, vz, bx, by, bz, and then take the determinant of this. You will get q v cross b, multiply that with q. Therefore, from there you will get q v cross b. Okay, but here if you see only I and j are there, so we can directly also write cross of that. So that will be easy in this particular case. Let us do that. Okay, B is given, velocity is given, we need to find the force. So write it, Q V cross B. Q, what is V? V is B naught I cap plus 2 B naught J cap. Sorry, first V cross B. So what is V? V is 3 I cap plus 5 J cap cross, this is B naught I cap plus 2 B naught J cap. Okay, so this is Q into 1 by 1, I cap cross I cap is 0 anyways, I cap cross J cap is K cap. So this will become 6 B naught J cap, 6 B naught K cap, sorry. Yeah, 6 B naught K cap. J cap cross I cap is minus K cap. So minus 5 B naught K cap. J cap cross J cap is anyway 0. So what it is from here? This is B naught K cap into Q. Q into B naught K cap. Charge of electron is E. So this will become E into B naught K cap. And this force is given as 5 E K cap. So I got from here that B naught comes out to be 5. So B naught is 5 Tesla. Is this clear? This question was very easy. Okay, need not write matrix because only 2 are there. If 3 are there, I, J and K are there. So taking 1 by 1 like this will take longer time. Then better way is to draw the matrix. Okay, and then take the determinant of that matrix, and solving that way will be very easy. Okay, another question. An electron is allowed to move with constant velocity along the axis of current carrying straight solenoid. Current carrying straight solenoid is there. If nothing is mentioned, in means take that solenoid to be by default a long solenoid. The magnetic field inside that is uniform. Okay, now a charge particle is moving with a velocity in the direction of the, you can say, solenoid, in the direction of axis of the solenoid, means the velocity is parallel to the magnetic field. What it means? Velocity is parallel to the magnetic field. If velocity and magnetic field are parallel, the magnetic force is 0. Force is 0, it means the particle will keep on moving in the straight line without any deviation. Come to the options. The electron will experience magnetic force along the axis of the solenoid. This is incorrect. The electron will not experience magnetic force. This is correct. The electron will continue to move along the axis of the solenoid. This is correct. It will continue to move with constant velocity. The electron will be accelerated along the axis of the solenoid. This is incorrect. The electron will follow parabolic path inside. This is incorrect. So correct options are B and C only. B. You see how simple questions are there in mains? How much easy questions are there? How much time we need to spend to solve this question? Hardly 20 seconds. Not even 20, I'll say 10 seconds. In paper, if you are like when you are there in the exam, so you have that focus, that time, and you have that speed. Okay, so very quickly you can solve this question very easily. Another question. A proton and an alpha particle of same velocity enters in a uniform magnetic field which is acting perpendicular to the direction of the motion. It means they are going to move in a circle. If they are moving into a circle, the ratio of the radii of the circular paths followed will be, you know the formula of radius, okay, the charges relation, you know, alpha and proton, the mass relation, you know, okay, you can find the ratio of the radius. Do it quickly, pause this video, solve this, comment your answer, and then you can resume this video. Okay, I hope you are back. So radius formula is V divided by omega, BQ by M. I always remember it like this. So therefore I am saying just remember omega. Omega is BQ by M. Radius is V by omega. Time period is 2 pi by omega. Okay. Now what I need to find? Ratio of radii of circular path described by alpha particle and proton. So if proton charge is E, alpha particle is charge 2E. Okay, you know that is He 2 plus. So if proton mass is m, alpha particle mass is 4m. This is nuclei of helium. Okay, and what else? Speed, same velocity. Velocity is same. It is mentioned. Velocity is same. Magnetic field is same. So anyways, these two things are same. Just take the ratio of the masses and the ratio of the charges. So if I write it first, I need to find for alpha to the proton. So first of all, the ratio of the mass. So this is 4m by m. Divide by ratio of the charge. So that is 2e by e. Clear? Yeah. So this comes out to be 2:1. 2:1. C option is there. Wrote the formula of radius. Now here mass is coming, ratio of the masses for alpha to the proton. So 4m by m. Second, charge is in the denominator. Okay, so divide by the ratio of the charges. So 2e and e will be in the numerator. We'll cancel it. This will become 2:1. These questions are asked, these type of questions like proton, alpha particle is there. Many times I have seen such questions in mains. Maybe some other particle might be there. Another question. An electron with energy 0.1 kilo electron volt moves at right angle to Earth's magnetic field, means it is moving in a circular path. The frequency of the revolution is time period formula, I know. 1 by time period is frequency. So frequency is basically 1 by time period is 2 pi by omega. 2 pi by omega bq by m. Okay, so this is basically bq by 2 pi m. Put the values. It is independent of the energy. Okay, it is independent of this. Need not that value is not required. Now Earth's magnetic field value is given to us as 1 into 10 to the power minus 4. So 10 to the power minus 4 into charge. It is electron. So 1.6 into 10 to the power minus 19 divided by 2 pi 2 into 3.14 into the mass. What is the mass? 9 into 10 to the power minus 31. And then you can solve it. Okay. Make sure you put your answer in the comments after solving it. Now you are mentioning all the answers. How will I get to know which answer you are talking about? So you can mention a bit about that, like what is that? The frequency of revolution, that I'll get, because frequency question is one only. So frequency is this. I'll get option is here. I think option D might be, isn't it? It will become somewhat what, 10 to the power 6, yes, and near about 3, yes. So D will be the correct option here. Another question. A region between y is equals to 0 and y is equals to D contains a magnetic field that is B into z cap. The particle of mass m and charge minus q enters the region from origin with velocity this. D is given to us, the deviation of charge particle in degrees at the point of its emergences. So these type of questions are also sometimes asked, not very frequently. Like some region is there of magnetic field, a charge particle is coming outside and then entering the region from outside, and then it is moving some distance inside the region and then going outside. And here you need to find the deviation. So basically let us show everything first. Let us draw the diagram, because when you will draw the diagram, you will visualize what exactly is happening here. So the magnetic field is between y is equals to 0 and y is equals to D. So let me take, this is my y is equals to D. Okay, let me take, this is my y is equals to D and this is my y is equals to 0. Magnetic field is in which direction? Z cap. So this is outside. Okay, so I'll say dot. Magnetic field is B. The particle is starting from origin with velocity v naught I cap towards the right. It is having velocity, let me take a different color. It is having a velocity v towards the right, v. Now this D is given to us and this d is given in terms of mass, velocity, charge and magnetic field. So I can relate this with r basically. What is r? R is equals to v by omega. This is my r. So d is basically r by 2. This is r. Okay, d is basically r by 2. I'm using small r, so let us write this in terms of small r. So r by 2. So this is basically half of the radius. So here if you see how the particle will move, q v cross b, and this is negative, so force will be in the upward direction. The center will be somewhat here, okay, a bit above, somewhat here, because this is r by 2, somewhat here, and the charge particle will move like this, not like this. It will move like this till it is inside the region of the magnetic field. After it comes, it will move in straight line. After coming out of the magnetic field, it will move straight line because there is no magnetic force then. Okay, how much total deviation is there? Okay, now let us see. Initially this, okay, and then it is getting out of the magnetic field at this particular point. This is r by 2, it means this is also r by 2. This is r radius. How much is this angle? R cos of 60. It means this angle is 60 degree. This is 60. This is 90. This is 90. How much is this angle? 60, 30, 60. 60 degree. So it deviated by an angle of 60 degree. Okay. Going like this, it turned by an angle of 60 degree till it reached here. After that, it is moving in a straight line. No deviation after that. So I will say the deviation here is 60 degree at the point of emergence. This question was, you can say, a bit thoughtful. You need to see how the charge particle is moving, how it will exactly exit, how much deviation is coming. You can draw like this in terms of the distance you need to mark first in terms of the radius, then only you can analyze this. Another question, a particle of charge q mass m is moving with a velocity that is minus vi cap towards a large screen. Okay, the distance is d. If there is a magnetic field b, that is b naught k cap, the minimum value of v for which the particle will not hit the screen. Okay, let us draw the diagram first, how everything is happening. Let us draw the diagram. The particle is moving along negative y-axis and it is going to hit a yz plane. Let me show yz plane. This is my yz plane, okay, like this. And the charge particle is coming like this, minus v naught I cap, na? So this is coming with velocity v. Now here magnetic field is out of the plane, k cap. Magnetic field is out of the plane. In which direction the force will be there? Q v cross b. Force will be in the upward direction. Force will be in the upward direction. So it will move somewhat like this in circle. So to just prevent it from hitting, it should turn like this. It means how much is this, or how much is this distance? Equal to radius. This distance should be equal to the radius. The minimum distance r should be equal to the minimum distance, initial distance I'll say, that should be equal to r. Okay, means I'll say just preventing it from striking. It can be greater also, okay, then it will turn before only. But for the minimum case, if I talk about, it should be just equal to r critically. Now we need to find the minimum velocity v. What is r? R is basically v by omega. R minimum is this radius, okay. So from there I can find v minimum. What is v minimum? V minimum just r divided by r into bq by m. That is my v minimum. Okay, what is this? Here it was mentioned that the distance between Yeah, towards a large screen placed in YZ plane at a distance d. This distance is given to us as d. So I'll keep this as d. So d into bq by m. D into bq by m. C option. Okay. B is, it is B naught K cap. So I'll put B naught there. Very easy. Yes. Another question. The figure shows a region of length L which with a uniform magnetic field of 0.3 Tesla in it and a proton entering the region with velocity 4 into 10 to the power 5, making an angle 60 degree with the magnetic field. Okay, here this is how it is entering the magnetic field in the horizontal direction. Now how it will move after entering the region, which condition it is having some angle with the magnetic field. So some component in the direction of magnetic field, another component perpendicular to the magnetic field, so it will move in a helical path. Okay, helical path like this. That is clear. If the proton completes 10 revolutions by the time it crosses the region shown, region shown, L is close to, how much is this distance L? Here it is mentioned that it completed 10 revolutions in that. 10 revolutions. If I say time period is t, so total time to cross it will be 10t. So total time to cross is 10 times of the time period. How much will be the total length? I'll say the total length will be my time period into the velocity. What is velocity? V cos 60. Simple. Okay, so what is L? L is V cos 60 into the into 10t. So 10 into what is t? 2 pi by omega. Like this. Okay, and now we can put the values to solve this. What is V? Basically V is 4 into 10 to the power 5. Yeah. Cos 60 1 by 2, 10 into 2 into pi 3.14 into m. M is mass of the proton that is given. Okay, divided by B. What is B? B is 0.3 into Q. Q is charge of the proton, that is 1.6 into 10 to the power minus 19. Make sure you solve it and put your answer in the comment section. Moving ahead, a beam of protons with speed 4 into 10 to the power 5 enters a uniform magnetic field at an angle of 60 degree to the magnetic field. The pitch of the resulting helical path of the protons is, pitch formula we already mentioned that. What is pitch? So pitch is equals to the time period into the horizontal velocity. Okay, horizontal component, what is that? V cos theta. Time period is 2 pi by omega into V into cos of theta, the angle of the magnetic field. Okay, at an angle of 60 degree to the magnetic field. So you need to check which angle he is talking about. Is that angle between velocity and magnetic field or somewhat another angle? Okay, it may mention like velocity is in this direction, magnetic field is at this particular angle. So try to read it properly. So therefore here this theta is the angle between velocity and magnetic field, and we got that as 60. So cos of 60. Now put the value. What is m? M 1.67 10 to the power minus 927. Charge we know, magnetic field 0.3. Okay, and velocity is 4 into 10 to the power 5 into cos of 60. Okay, here also somewhat same things. 4 into 10 to the power 5. Here also the velocity is 4 into 10 to the power 5. Anyways, you can solve it. Now motion in combined electric and magnetic field. Now we are taking effect of both the electric and magnetic field. So the total force, if I talk about, it will be the sum of the electrostatic force and the force due to magnetic field, that is QV cross P. Now you need to see in which direction electric field is there, in which direction the magnetic field is there, in which direction the resultant force will be there, and how the particle will move. As I mentioned, like when I was talking about the non-uniform pitch will be there when in helical motion case. Let us take, I mentioned there is electric field in the direction of magnetic field in that particular case. So there can be a non-uniform pitch. So you'll get, oh, this is how the particle will move. And if, let us take, the magnetic field is there in particular direction, the electric field is there in another direction, then individually see how they will try to move the particle and how the particle will resultantly move. Okay, this is what you have to do. So velocity selector, this is different conditions we are talking about. So velocity selector means a beam of, let us take, charged particles are there. In a beam, all the charged particles will not have the same velocity, their velocity will be different. I need only those particles which has precisely this velocity. How will I choose that? How will I choose that? Because it is very difficult to segregate. How will I choose that? So that can be done like, what I will do is, let us take a charged particle is having charge q, velocity v, it is moving in this direction. I applied electric field in upward direction, let us take E. So the force due to electric field will be in which direction? In this, that is q into E. I want to move it straight, it means the magnetic force should be in the downward direction. F magnetic should be in the downward direction. So q v cross b should come in the downward directions. So q v cross b, okay, b is coming out to be q v cross b, b should be out of the plane, then only the force will be in the downward direction. So here my magnetic field, let us take, is out of the plane. Out of the plane I can show it dot, okay, or I can show it like this. You should understand this vector is out of the plane, this is my b. So q v cross b, magnetic force is in the downward direction. How much is the magnitude? bvq. And let us take the particle is moving undeviated. Undeviated means both the forces are equal, cancelling each other. So q is basically equals to bvq. Okay, so I got the velocity to be E by B. So what I will do is, basically I'll apply electric field and magnetic field in a direction perpendicular to each other and perpendicular to velocity, and I'll keep the ratio of the electric field and magnetic field equal to the velocity which I want. So what will happen? Those particles will just move straight forward. I applied that. Those particles which are having this speed, let us take a beam is like this. Those particles which are having this speed, they will move straight. They will move straight. Those particles which are having lesser velocity, it means electric force will be higher. Force due to electric field will be higher. They will deviate like this. And those particles which are having greater velocity, force due to magnetic field will be higher. They will deviate like this. Let us take this speed was my v naught. Okay. So this is v greater than v naught. This is v less than v naught. And this is v is equals to v naught. This is how I am able to segregate only those particles which are having velocity equal to v naught. And this particular, you can say, setup is known as the velocity selector. We can select particular velocity from a beam of large number of particles which are having maybe like so much different velocity in that particular collection. Now, also there can be different you can say conditions also of electric field and magnetic field. There can be like both electric field and magnetic field are in the same direction. Okay, and let us take, if you release the particle from rest, so how it will move? My electric field is in this, I'm talking about another conditions. Let us take my electric field is in this direction and my magnetic field is in this direction. Okay, and I am leaving my particle, charge particle here with zero velocity. What will happen? electric field will apply a force initially, because initially magnetic field force will be 0, velocity is 0. So electric field will apply a force. In which direction it will move? Towards the direction of electric field. So it will move in this direction. Velocity will keep increasing due to the presence of electric field. Magnetic force will always be 0 because the velocity is parallel to the magnetic field. So the particle will keep on moving in the straight line. But with, you can say, variable speed, speed will keep on increasing. And there can be, like, there are not so many varieties of these particular conditions that are asked in JEE mains. Okay, therefore I'm not talking about you can say different thing, their cycloidal path and all those things. So that is not required. And yeah, move to the questions. A proton moving with a constant velocity passes through a region of space without any change in its velocity. Okay, if E and B represent the electric and magnetic field, then the region of space may have. Without change in velocity means the total force on the particle should be 0. So see the conditions where the total force on the particle can be 0. First case, E is 0, B is 0. Both forces will be 0. Electric force also 0, magnetic force also 0. It can pass. Yes, this is true. Second condition, E is 0, B not equal to 0. Now electric field is 0 and magnetic field is in the direction of the velocity. Then what will happen? Particle will move straight. This also can happen. Third condition, magnetic field is 0 but electric field is not 0. So electric field will apply some force and that force cannot be cancelled by magnetic field. It means it cannot move with the same velocity. Okay, it cannot move with the same velocity. Velocity will change. This is incorrect. D option, E not equal to 0, B not equal to 0. It can be the condition of velocity selector. As we discussed, both the forces can cancel each other. This can happen. So I can say A, B and D. These all three can be the correct options. Another question. A particle of mass m, charge q, has an initial velocity v naught g cap. If the electric field is this and magnetic field is this, act on particle, its speed will double after a time. Now, in this you need to visualize a bit, like how the particle will be moving. You need to visualize. Okay, let us visualize that. The particle is having velocity j cap in the direction j cap, means like this. The electric field is towards the right, E naught I cap. So electric field is this. Magnetic field is also I cap. Magnetic field is this. Now let us consider only magnetic field is there first. How the particle will move? Particle will move in circle like this. Okay, it will move in circle like this because velocity is perpendicular to the magnetic field. Now horizontal electric field is added. What will happen? Slowly it will gain horizontal component of velocity. It will move in a helical path with variable pitch, isn't it? It was moving in circle. You switched on a horizontal electric field. Horizontal velocity will keep on adding and it will move like this in a helical path with variable velocity. So when the velocity will become double. Now due to electric field, in which direction it will gain the velocity? In the horizontal direction. How much velocity should be added in the horizontal direction such that the resultant of these two will become twice? How much it should be added? So you will say here Vx should be equals to root 3 V naught. What is Vx? Vx is Ax into time. He was asking time only, okay? Yeah, Ax into time. What is Ax? Electric field into the charge, that is the force, divided by the mass. So root 3 V naught is equals to here electric field into the charge divided by the mass into time t. Everything is fine? Yeah. So time comes out to be root 3 V naught m, root 3 V naught m divided by q E naught. Okay, there is some mistake. It should be root 3 here. Yeah, it should be root 3 here. Let me write with some dark color. This should be root 3. C comes out to be the correct answer. Okay, so you have to visualize. If the two things are coming, you need to visualize. First take the effect of one, then take the effect of another, and then see how resultant it should move. That will help you to solve question in a better way. Another question. An electron is moving along x direction with a velocity 6 into 10 to the power 6. It enters a region of uniform electric field 300 volt per centimeter, pointing along plus y direction. The magnitude and direction of the magnetic field in this region such that the electron keeps moving along x direction will be. Okay, so first of all, if I talk about here, when you are reading this question, if you are reading this question like me, then after that at the end you will be lost, like what it was saying, in which direction, everything is there. So when you are reading the question, draw the things. So electron is moving along plus x direction. So electron is moving like this. The velocity is given with v. Let us take this velocity as v. Then enters a region of uniform electric field pointing along plus y direction. Electric field is pointing along plus y direction. Okay. The magnitude and direction of magnetic field set up in this region such that electron keeps moving. It means it will have an electric field. It is having electric field in the upward direction. It will have force due to electric field in which direction? In the downward direction, because charge is negative, therefore opposite to the direction. Therefore magnetic field should cancel the electric field. Magnetic field should cancel the force due to electric field, not electric field, cancel the force due to electric field. So here I am saying this is my electrostatic force. Okay, so the magnetic field force should come in this direction, force due to the magnetic field. And Q V cross B, Q V cross B. So V cross B should come in the downward direction, then only Q negative consider. If we consider the negative sign, it will come in the upward direction. So V cross B, V cross B. So B should be out of the plane. B comes out to be out of the plane, dot. So out of the plane means plus Z direction, plus Z direction. Okay, A and C, two options are there. And then you can find the magnitude. Just equate the two magnitudes. You will say EQ is equals to BVQ. I need to find the magnetic field, that is E by V. What is E? 6, okay, this is 300 volt per centimeter. I need to find per meter. So this is 300 into 100. Okay, so this is 300 into 100 divided by, the velocity is 6 into 10 to the power 6. So 6 into 10 to the power 6. How much is this? 10 to the power 4. 10 to the power 2 will remain there. Okay, 3 into 2. So this is 100. Everything is fine, yeah. This is 100 divided by 2. Oh, I did a mistake, I think. Oh, not 100, that is not 100, that is 10 to the power minus 2 in the numerator. This is 10 to the power minus 2 divided by 2. So what it will be? It will be 5 into 10 to the power minus 3. 5 into 10 to the power minus 3 Tesla along positive Z direction. C is the correct option. Okay, yeah. First of all, we got the direction. How we got the direction? Seeing the direction of the force due to electric field, that is in the downward direction. So magnetic field force should be in the upward direction. Q V cross B should come in the downward direction. Q V cross B, okay, in the downward, then only Q into BV will be in the upward direction. Like V cross B in the downward, Q is negative, so it will become in the upward direction. So magnetic force is like this. Okay, now magnetic force on a current carrying conductor. We discussed magnetic force on a charged particle. Inside a current carrying conductor, charged particles are moving, electrons are moving. Okay, so resultant force will be there. Like we can find the individual forces on each of the charges, and then we can take the resultant of that. That will give us the resultant force on a current carrying conductor. I am considering a current carrying conductor like this. It is having some current in this direction I. Direction of current represents the direction of motion of the positive charges. Basically, motion of the electrons is opposite to the direction of the current. So, I can consider my positive charges to be moving in the right direction, plus Q. Although the positive is not moving inside the conductor, you know that. Although the electrons are moving, but effectively we can consider the positive charges moving towards the right. Okay, charge Q. Having velocity V, what is that V? V will be drift velocity. The effective speed will be the drift velocity. Okay, so it is moving with the drift velocity Vd. How much will be the force? Force on this particular charge particle. Okay, force on this particular charge particle is Q V cross. So V drift Q V cross B. Magnetic field is there in some direction. So this becomes my force. Okay. Now on this one particle is there. Now I am taking a small length dl. How much is the force on that particular length? This is, let me denote this f with a small f. Okay. Let me denote this f with a small f. This was force on one of the particle. Now how much will be the force on this length? So many charge particles are moving inside this length. So many charge particles are moving. So what you can do? This force on one charge into the number of the charge particle. So if I say total force on this, let us take the force is df. What is that? Force on 1. Force on 1 is Q V cross B. Force on 1 into the number of charge particles. How many number of charge particles? Here I will define like the charge density or number of charge particle per unit volume is n. Okay, this is number of charges per unit volume. So per unit volume thing is clear to us. Okay, so n into the volume. What is the volume? Volume is length dl into area of cross section. This is not a cross product, I am just multiplying it. Let me write it together. Okay, number of charge particle per unit volume into the volume, A into dl. Now here if you see this n E, the charge, A into V drift cross B into dl. And what is this? The current I. Okay, so this will become my I dl cross B. This is my df. I dl cross B. And if I need to find the total force F and integrate it, the total force on the conductor will be integration of I dl cross B. So if magnetic field is B in a region, I need to find the total force on a conductor, integrate I dl cross B. But in mains, you need not integrate. Why so? In mains, the questions that are asked for force that are most, I'll say most likely for uniform magnetic field. So in the formula, when I'm saying that my F is basically integration of I dl cross B. So if magnetic field is uniform, okay, so for uniform magnetic field, B will be constant. Okay, just you need to integrate dl. I is my constant in the conductor. Just you integrate the dl. Okay, integration of dl will become your L effective. So it will become just I L cross B. Let me write it together properly. So this is I L cross B. What I am talking about here, what is effective length? Let us take a conductor is like this, carrying a current I. Magnetic field is uniform here, that is uniform. I need to find the force. So when I'll take the L, the effective length means this is the beginning, this is the end, this is basically my L. Just connect the beginning and the end. Doesn't matter what is the shape of this. Doesn't matter what is the shape of this. Okay, if the magnetic field is uniform, just take the effective length. Just connect initial and final. If it is a closed loop, force will be 0. Okay, if it is a closed loop, force will be 0. Now here it is very interesting to know that even if the shape is like this, the force will not change. Okay, even the shape is a straight line, like just connecting that and that, the force will not change. It will be the same. Okay, but the point is this L effective method will be applicable only when the magnetic field is uniform, and in mains you will get questions only from the uniform magnetic field cases. Okay, where the magnetic field will be uniform only. So now next, force between two parallel current carrying conductors. So let us take, we are having two parallel current carrying wires and we need to find the force between those. Let me take, this is one, this is another, having current I1, I2 in the same direction, separation is D. Okay, we are considering that they are very long. And what we will do, we need to find force on one due to another. So I can find force on any one of them. On the other, the force will be same in magnitude. So let me find force on this second due to the first. Okay, so what I need to do, first I need to find what is the magnetic field there. So due to this, if I find the magnetic field that is inside the plane. Okay, this is magnetic field of wire 1. So what is B1? B1 is mu naught I1 by 2 pi into the separation, that is D. You know this formula, B is equals to mu naught I by 2 pi r. You know that formula. Okay, I am using that. So that is B1. That is the magnetic field on wire 2 due to wire 1. Magnetic field I know. Now what I need to do, I need to find the force. So IL cross B. Okay, IL cross B. So force is in this direction. So I am taking a small, let us take a length here, L. Okay, so on this length, if I want to write the force will be in this direction, F. And how much is that? F is IL cross B, and the angle is 90 degree only. So F comes out to be BIL. So B, what is B? B1, okay, into I, current of second, this wire on which I am finding force, I2, into the length L. So what is B1? Mu naught I1 by 2 pi D I2 into L. This is my force. Okay, and if I write force per unit length, F by L, so this is mu naught I1 I2 by 2 pi D. And this formula is important. You can remember this if it is possible for you, and if you cannot remember it, at least understand the concept so that you can quickly derive it. Very quickly you can derive it. Like it's not always it is possible for us to remember everything. Okay, it may not be possible. You may not like keep everything in the mind, but at least if your concept is very strong, so few of the things you can very quickly derive. Those things which cannot be derived very quickly, remember them. But if, let us take in exam, this question comes and you need to write the formula, what you can do? Quickly draw two parallel lines, write the magnetic field, force will become BIL, write the formula. That's all. And this is multiple times asked. Now one thing, if you see, force on this conductor is towards this, and if you find force on this, it will be towards this. Another one. So if the current is in the same direction, the two conductors are attracting each other. If the current will be in the opposite direction, they will repel each other. Okay, write that point, that conductors having current in the same direction, they will attract. Okay, so let me write current in same direction and second condition, current in opposite direction. So keep this thing in mind that they will attract and they will repel. This is asked. Yes, keep this thing in mind. Parallel, attract. Anti-parallel, repel. Okay, now questions time. Coming to the question. The horizontal component of Earth's magnetic field at a place is this. A very long straight conductor carrying current route to Ampere in direction from southeast to northwest. Yeah. The force per unit length experienced by the conductor is. So, the conductor is like this. From southeast to northwest. Yeah. And the horizontal component of magnetic field will be from south to north. Okay. So, my magnetic field is like this. This angle is 45 degree. What I need to find? The force per unit length experienced by the conductor. If I write the force IL cross B, BIL sine theta, that is the magnitude. Theta, the angle between the two is 45 degree. Okay. What is I is root 2. So root 2 and 1 by root 2 will get cancelled. And B into L. This comes out to be force. Force per unit length. This is equal to the magnitude of magnetic field. What is that? That is 3.5 into 10 to the power minus 5. So this comes out to be 35 into 10 to the power minus 6. This is 35. Simple? Yeah. Okay. Another question. Now, here a rigid wire consists of semicircular portion of radius r and two straight sections. The wire is partially immersed in a perpendicular magnetic field, that is B naught J cap. Yeah. As shown in the figure, the magnetic force on the wire is. Now, force is only in this section. Magnetic field is uniform or non-uniform? Uniform. Just take the effective length. So this is the beginning. I am joining the ends which are inside the magnetic field. Okay. This is the end. So this is my effective length. My current is in this direction now effectively. How much is the effective length? 2r. R is radius here. So this is 2r. So effective length is my 2r. This is 2r. IL cross B. IL cross B outside. Okay. It is in the downward direction. So force is coming in this direction. And that is B, IL, and B into I into L is 2R. Okay. So minus 2 BIR J cap, D option. Just using the concept of effective length. Other way also you can do. You can find the force on this upper semicircle. There you can use concept of effective length. And then you can find the force on these two straight conductors. Okay. When you write, they will cancel each other. Because for this, if you do IL cross, I need to use IL cross B. This is towards the right. And for this IL, okay, cross B, it is towards the left. So left and right, they are cancelling each other. Only the force is due to the semicircular part, and that you can write by taking the effective length, that is equal to 2IR only. Another question. Two long straight wires P and Q carrying equal current of 10 ampere each, okay, were kept parallel to each other at a distance of 5 centimeter. So they are P and Q are there, okay. This is P, this is Q. They are carrying equal current of 10 ampere, okay, kept parallel to each other, and they are at a distance of 5 centimeter. And this is 10 ampere. This is 10 ampere. Okay. Magnitude of magnetic field experienced by 10 centimeter length of wire P, okay. Magnitude of magnetic force experienced by 10 centimeter length of wire P is F1. Yes. Okay. So For 10 centimeter, the force is given to as F1. If distance between wires is halved and current on them is doubled, F2, the force on 10 centimeter length of wire P will be. So what is force per unit length? Force per unit length formula I already wrote, that is mu naught I1 I2 by 2 pi d. Currents are getting doubled, so this will get 4 times. Distance is getting halved. Okay, distance is getting halved, it means it will become 1 by 2, that will go in the numerator, so effectively it is getting 8 times. So the force finally will become 8 times of F1. Force is getting 8 times of the initial force. Clear? This question was asked in 2024. The parallel wire question is asked. Multiple times it is asked. Now let us talk about torque on a current carrying loop, and let us talk about magnetic dipole. So first of all, if a loop is there, current carrying loop is there, and that is placed in a uniform magnetic field, so how much will be the force on this? Can you tell in the comments? If the magnetic field is uniform, how much will be the force on a closed loop? That will be 0, as we discussed. Effective length is 0, so the force will be 0. So if a closed loop is there, and if you talk about the total force on that closed loop, I will say that is 0. But the torque may not be 0. So here we are finding torque. So let us take, we are having this closed loop. This closed loop is carrying current, and this current direction is this. You can see this is the direction of the current. So here current is like this, here the current is like this, here the current is like this, and here the current is like this. The magnetic field is there, and this magnetic field is in this direction, you can say in the upward direction, and it at this particular condition in which it is shown, the angle between the area vector means the area of this loop that is perpendicular to the surface of this, and the magnetic field, this is given as phi. Okay, the angle between the normal to the surface and the magnetic field is phi, and here we need to find the torque. So first of all, we have these 4 state conductors, 1, 2, 3, 4. One by one, let us find the force on each of the 4. So first of all, if I talk about, let us take this conductor. The magnetic field is, you can say magnetic field on this conductor I am talking about, okay, on this section, from here to here. On this section, the magnetic field is in which direction? Magnetic field is at an angle phi with the normal. So if I do IL cross B, the force comes out to be in this direction, F dash. And similarly, when I will do for the other one, for this conductor, if I do my IL, what is IL? IL in this direction, okay. IL cross B, the force is in the opposite direction, minus F. And these forces will cancel each other, you can say equal and opposite. Now, if I find the force on this conductor, let us take, here the current is in this direction, so IL cross B, the force is in this direction, F, and on this conductor IL cross B, the force is in this direction here, and these two forces will cancel each other. Total force is 0, that we understand. But I am talking about torque. Here torque will be non-zero. If you say, let us find the torque about this axis of the loop. So the torque due to the F dash and this force and this minus F dash, they'll anyway cancel each other, okay. So that is also along the same line. So anyways, we'll say that the torque due to this and this will be 0. Now the torque due to this and this will not be 0. That will actually add up basically. How? Let us do that. Here force is in this direction. Magnetic field, if I say this was IL, okay, and cross B. So let me visualize a bit properly. So this is my IL and this is cross B. So the force is coming out to be in this direction. And here the force is coming out to be in this direction. Now about this axis, if I want to find the torque due to this force, so what I will do, I'll take the perpendicular distance. What is that perpendicular distance? That is, this distance is B by 2, okay, this is B by 2. So the perpendicular distance, about this axis I am saying, so the perpendicular distance is B by 2 into sine of, that is this distance basically, okay. How much is that? That is B by 2 into sine of phi. Okay, so what it will become? This is my F into B by 2 sine phi. Okay, and similarly the same will be due to that and both will be adding. Okay, so into 2. So what it is? Basically this is F into B into sine of phi. What is B? B is IL cross B. Okay, so this is what is this length? This length is my A. Okay, so A into I into the magnetic field B into the small b into sine of phi. It becomes like this. Okay, yeah. So what is B into A? This becomes my area and this I is my current and this is B into sine of phi. This becomes my torque. Is this clear? Now you may say, I didn't consider the torque due to this two, because if you see IL cross B, the force was in that direction. Okay, so about this axis, that torque is 0, and similarly about this torque is also 0. So both torque due to these two forces is 0. Due to these two, the torque is adding. So I wrote the total torque like this. Is this clear? A bit difficult to visualize in this diagram. A bit difficult. You may draw the side view. The side view will help you. If you draw the side view like this, okay, you can draw the side view of this. You are having this force F. You are having this force F. Okay, and writing the torque. So this perpendicular distance was my B by 2 sine phi, and this perpendicular distance is also B by 2 sine phi. This force is this my BIL, so that was my length A into I into B. Same, this also A into I into B. Okay, now write torque about center. So this is B by 2 sine phi into F. Okay, same, B by 2 sine phi into F, both will add, total comes out to be this. Side view is better to visualize, I am saying, but in side view you cannot see this torque due to the force on this and this. Okay, therefore I drew it like this so that you can see that torque due to this is also cancelling. But when you are writing the total torque, draw the side view, better to visualize. You can directly write the torque, because in 2D it is easy to visualize. This is 2D, this is 3D. In 3D you might be confused, sir, how you are writing that as B by 2 sine phi, that thing. What was phi? Phi was my angle between the magnetic field and the area vector. Okay, now this thing I into A, this we write as the magnetic moment. Okay, this is my magnetic moment of this loop. Magnetic moment, or we call it magnetic dipole moment. Okay, and this is a vector, and basically we denote that with M, and this is my I into A. A is also vector. What is the direction of that vector? Perpendicular to the surface. Okay, so M is basically I into A. And if let us take, there are number of turns also. I am considering here the turn is to be 1. If let us take there is n number of turns, we say the magnetic dipole moment to be NIA. Here N becomes my number of turns. This is MB sine phi. What is that? M cross B. MB sine phi. This is M cross B. Why I did this derivation? This was not required. I wasted time. Why so? In electric dipole, we know the torque. What is that? Torque is P cross E. So when you writing the torque due to magnetic dipole, just take magnetic dipole moment instead of electric dipole moment and write magnetic field instead of electric field. That's all. You remember that formula? For electric dipole, we wrote torque as P cross E. Okay, this was for electric. When I am writing here the torque, okay, on the magnetic, so used instead of electric dipole moment, use magnetic dipole moment M. Instead of electric field, use magnetic field cross B. Just M cross B. You got the formula directly. Okay. So magnetic dipole moment we wrote as M, and M is my NIA, where I is the current, A is the area, N is the number of turns. If turns will increase, magnetic dipole moment will increase, current will increase, magnetic dipole moment will increase, or the area increases, the magnetic dipole moment will increase. Okay, any of the things you can increase, you can vary to vary the magnetic dipole moment. Now, what is the direction of magnetic dipole moment? If I talk about that is the direction of area, basically you can see. Okay, but let us take, if I talk about a circular loop like this, carrying current like this. So what is the direction of magnetic moment? Out of the loop. Okay, move your thumb, move your fingers in the direction of current. So the direction of thumb, that is here out of the plane. So here the direction of magnetic moment is out of the plane. If the current is, let us take in clockwise direction, it will be inside the plane. This is the direction of M. Need not be circular, this can be some rectangular shape also. If let us take some shape is like this, some shape is like this, here also you can say the magnetic dipole moment is inside. Formula will change. Here if I say magnetic dipole moment, this is my current I into the area pi r square. Okay, here also I into the area pi r square. Here I will say this is I into the area is this side A, this side B. So this is A into B. Okay. So just it is NIA. Keep this in mind. Sometimes number of turns are also given and we miss that. Now circular current loop as magnetic dipole. So as we discussed, circular. As we discussed, this, let us take a current carrying loop having current like this. Here magnetic dipole is out of the plane. It is out of the plane. If it is clockwise, that will be into the plane. Now in electric dipole, we used formula, we showed dipole like a arrow like this. Okay, then we say like this is my electric dipole moment. This is how we used to show, and we used to show that from negative charge to positive charge. In this, if my loop is let us take this. Loop is this. I show the magnetic dipole moment, or I represent it like this. This is my magnetic dipole moment. Okay. And if you remember, like if you have seen my video on electric charges and fields, then you remember everything. Then if you know that on the axis, if a dipole is like this P, on the axis, if I talk about at a distance r, what is the electric field? You'll say, sir, here the electric field is 2 kp by r cube. This is my electric field. So here, if I say on the axis of the dipole at a distance r, what is the magnetic field? So here I'll say my magnetic field is 2kp by r cube. I'm just replacing, okay, 2k. There the constant is k, here the constant is mu naught by 4 pi. So k is mu naught by 4 pi. P, I'll write m by r cube. So by r cube. This I wrote on the axis. Okay, this is for axis. On the equatorial line, at a distance r, if I write the magnetic field, you'll say this is minus kp by r cube. Similarly, here on the equatorial line, let us take somewhat at a distance r. I'll say that it will be in the downward direction. What that will be? So this is equatorial. So the magnetic field there will be minus k is mu naught by 4 pi into p divided by r cube. Sorry, not p, that is m divided by r cube. But this formula when we derived, we assumed that this r is very large. Okay, r is very large as compared to the distance, or I'll say the distance between the two charges. That assumption was there. Here also this r should be very large as compared to the radius. This r should be, this distance should be very large as compared to the radius of the loop, current carrying loop. Then I can use this formula. Do I need to remember this formula? Don't remember this formula. Don't remember this formula. Remember the formula for electric field on the axial and on the equatorial. Using that you can write it. Okay, don't remember separately. That is not required. Okay, now let us discuss about magnetic dipole moment of a revolving electron. Now electron is revolving, so effectively charge is moving in a loop, effectively a current is moving in a loop, effectively it will also have its dipole moment as we discussed for a current carrying loop, same thing. Okay, so what is dipole moment? Dipole moment m, this is equals to current into the area. Current, I'll say current is charge per unit time. This is how we write. So charge here E, and the time it takes to revolve it completely, or you will say if I am taking any cross section, how much charge passes? E. In how much time? The time period of revolution. What is that? 2 pi r by v. Into the area, pi r square. So pi, this r, this is EVR by 2. This becomes my magnetic moment, dipole moment, multiplying and dividing with m. MVR. MVR is, what is MVR for a particle? That is the angular momentum of the particle. So this is E into L by 2 into m. EL by 2m. L is the angular momentum. Okay. Or if I write from here m by L, that is E by 2m. Not m by L, let me write m by E. Anything I can write, that is also correct. L by 2m. Okay, I wrote it, we'll use it again in a while. So basically this is how we can find the dipole moment of an electron. The direction, you can see the electron is moving like this. So we will not take the direction of the current like this, opposite. So here it is inside the plane. So that is inside the plane, cross, inside the plane. Okay, now the magnetic dipole moment of a revolving charged insulating ring. Let us take an insulated ring is there. Let me draw a ring. This is insulated ring. Here charge Q is distributed uniformly like this. Charge Q is distributed uniformly on the circumference. Now let us take it as rotating, revolving like this with omega. Here if I ask you, write the dipole moment, magnetic dipole moment. So just use the formula. I'll say magnetic dipole moment is equals to current into the area. Current is charge divided by the time. Time is 2 pi by omega, time period. Okay. Total charge Q will pass through a cross section in one complete time period. Complete time period 2 pi by omega. Into the area. Area is pi into r square. Let us take the radius to be r. This becomes my dipole moment here. Okay. And now, wait a minute. This is Q into omega. Okay, 2 pi by omega into pi r square. Anyways, this pi is getting cancelled. So this comes out to be Q into omega r square by 2. Let us divide and multiply with m. Okay. And here this mr square omega. This is my I omega. This becomes my angular momentum. This is Q into my angular momentum divided by 2m. So I can say that m by L is basically Q by 2m. Here also mentioned that m by L we can mention, or other way also you can mention. Anyways, let me mention the same way. M by L is basically Q by 2m. Okay. So m by L, the ratio of magnetic dipole moment to the angular momentum comes out to be Q by 2m. And this is maintained everywhere. Even if you take a charge disk, rotating charge disk, there you find the magnetic dipole moment by integrating. Okay. And you see the ratio will come out to be Q by 2m. You take a hollow sphere, okay, the charge on the surface, non-conducting, rotate it, you will get the same answer. The ratio will be Q by 2m. Magnetic moment m will be different. So you can use this ratio to find the magnetic dipole moment even. If a solid conducting sphere is there, that conducting sphere will effectively behave like a hollow sphere because charge is on the surface. If a solid non-conducting is there, then it will behave like a solid sphere only. There you need to consider the angular momentum accordingly, because moment of inertia is there, na, I. So accordingly you have to consider I. But that much is not required for means. Don't go into that much deep. In advance a question was asked. Last year in advance a question was asked. So there was one hollow sphere. Okay, the charge was on the surface, and another was a solid surface. The charge was distributed in the volume. We need to find the relation between that. So that was for advance. It's not much required for mains. You can just understand for a ring. Now, torque on a magnetic dipole in external magnetic field, we already discussed. For electric dipole, we wrote the torque as P cross E. So here for magnetic dipole, if we write torque, that will be M cross B. In place of electric dipole moment, we write the magnetic dipole moment. In place of the electric field, we will write the magnetic field. So try to remember the formula by relating it like this. So that you will remember both the formulas for electric field chapter also, for this particular chapter also. Okay, let us have this question. We are having a uniform magnetic field of 2 into 10 to the power minus 3 Tesla acting along positive y direction, a rectangular loop of side 20 centimeter and 10 centimeter with current 5 ampere in YZ plane. Okay. Positive y direction, the magnetic field is in this direction. Okay. And then rectangular loop is there in the YZ plane. YZ plane means like this. I am taking x towards the right, okay, y upwards, z out of the plane. So YZ plane may become like this. Okay. The sides are given. The current of the loop is given 5 ampere. The current is in anti-clockwise sense with reference to negative x-axis. Negative x-axis means this is positive x, this is negative x. So in negative x, when I am saying the current is in anti-clockwise. Anti-clockwise means the current is going like this. The current is going like this. So this is the direction of my magnetic dipole moment. Current is in the anti-clockwise. When I'll move like this, the thumb direction comes towards me. So this is the direction of the magnetic dipole moment. Okay. Magnitude and direction of the torque is, go to the options. All the 4 options of the magnitude are same. So don't find the magnitude. Just see the direction. M cross B. M is towards right, B is y-axis, so M cross B inside the plane means negative z direction. So option comes out to be B along negative z direction. So in mains, many times this thing happens. Like multiple things are mentioned in the question, but just by seeing the options, you can reject many of the things. So just by seeing the options, I rejected calculating the magnitude. Just find the direction. Very easily we can just see and find it and click mark the answer. Even if you find the magnitude, that is not required. All the 4 are having the same magnitude. Now potential energy of magnetic dipole in external magnetic field. In electric dipole, we wrote potential energy as minus P dot E. This was the formula. So here if we write for magnetic field, so potential energy formula will be minus M dot B. Just see the relation. In place of electric dipole, I wrote the magnetic dipole moment. In place of electric field, I wrote the magnetic field. So potential energy becomes minus M dot B. Electric field is, let us take, magnetic field is in this direction. My dipole, magnetic dipole I am showing now, magnetic dipole, okay. My magnetic dipole is like this. It will have a torque like, it will try to turn in the direction of magnetic field. The same way we discussed for electric field also, okay. It will try to turn in the direction of magnetic field, means it will try to align it with the direction of magnetic field. It will try to align it with the direction of magnetic field, okay. So this is basically the stable equilibrium condition. You deflect from it, it will come back. And this I am saying this is stable equilibrium, okay. Stable equilibrium. Stable equilibrium means the potential energy is minimum. When it is minimum, theta is 0. Understand that way also, okay. Theta is 0 or potential energy is minimum. And if I put my dipole like this, opposite, just the opposite, it will become my unstable equilibrium. This is unstable. Unstable equilibrium means potential energy is maximum. When it is maximum, when theta is 180 degree. Theta is 180 degree. My potential energy is maximum. Getting it? Okay, now work done in rotation of magnetic dipole moment in external field. What will be the work done? Work done is equal to change in potential energy. So when we write work done, this is equal to just the change in potential energy. So you find final potential energy, find initial potential energy, take the difference, that will be equal to the work done. Work done, scalar, potential energy is scalar, okay. I'm not writing lengthy statements because we are just quickly revising everything. A coil having 100 turns, area 5 into 10 to the power minus 3, carrying current of 1 milliampere is placed in uniform magnetic field of 0.2 Tesla such a way that plane of coil is perpendicular to magnetic field. Perpendicular to magnetic field. Plane of coil is perpendicular to magnetic field. Theta is. Now this is the confusing part. Plane is perpendicular to magnetic field. Area vector is not perpendicular to magnetic field. If this is my, this is a coil, okay, anyways, you can consider like circular coil like this, some 100 tons. This is my magnetic field. So my magnetic dipole moment is also in the same direction. Plane is perpendicular, not area vector. Okay, so keep this thing in mind. Many times the angle is given between the plane and the magnetic field, and when you calculate the potential energy, you do a mistake. If the angle is given between magnetic field and plane, your angle between area vector and the magnetic field will be 90 minus of that. Okay. Such a way that the plane of the coil is perpendicular to the magnetic field. The work done in turning the coil through 90 degree is, okay. So initial potential energy formula first. What is that? That is minus m dot b. If I write initial potential energy, theta is 0, so minus mb. If I write the final potential energy, I am turning by 90 degree, so theta will become what? 90 degree, so that will come out to be 0. So when I am writing the work done is equal to u final minus u initial, that comes out to be just mb. What is m? NIA. M is number of turns into the current, into the area, into the magnetic field here. What is N? N is 100. What is current? 5 into, okay, no, this is not the current. What is current? Current is 1 milliampere, yeah, 10 to the power minus 3. What is area? Area is 5 into 10 to the power minus 3. What is B? B is 0.2. Perfect? Yeah, 0.2 Tesla, that is. So this will become minus 3, 10 to the power minus 6. We need to find in microjoules, so micro will come from there. And here 5 into 0.2, that will become 1. So this will become 100 microjoule. So this comes out to be 100 microjoules. Okay. Now SHM, simple harmonic motion of magnetic dipole moment in external magnetic field. We discussed same thing for electric dipole moment also. So we discussed, now I am doing that thing again actually for magnetic dipole. This is my magnetic field. I was having my electric dipole initially in the direction, sorry, not electric, magnetic dipole. I was having my magnetic dipole initially in the direction of magnetic field. Now I deflected by an angle theta. How much will be the torque? You will say torque is m cross b. That is mb sine theta. A negative sign will consider here. Why so? I am displacing in this direction, the torque is coming in this direction, that is a restoring torque. Therefore I am writing it like this, and this torque is equals to, this is angular oscillation, torque is equals to I alpha. I into alpha we write as minus omega square theta. I wrote minus because minus will get cancelled there, therefore I wrote it. Oh, why it is b twice here? This is minus mb. Okay, theta is very small, sine theta is nearly equals to theta, minus sign is getting cancelled, omega comes out to be root of mb by I, time period is 2 pi by omega, time period of oscillation becomes 2 pi root I by mb. Just similar derivation to what we did for electric dipole oscillations. Okay, same thing we are repeating again. It is, you can say, just a quick revision for your electric charges and that particular chapter concepts, the dipole concepts. Okay, now we are going to discuss about moving coil galvanometer. As we had previously discussed that galvanometer is generally used for current detection purpose. It measures current of very small magnitude also, that we had discussed previously, like it can show deflection up to a current of microampere, that ammeter will not show. Therefore we use galvanometer because even if a small current will be there, the galvanometer will show the deflection. How galvanometer basically works, that we are going to see here. Now let us take, you connected this galvanometer in a circuit. Current is going through the galvanometer, coming out. Here we have made loop, so magnetic dipole moment will be there, magnet is there, some torque will come. Okay, so some torque will come, it will turn, The needle was initially on 0 in between. Now some torque is there, it will turn. Now if nothing is there to stop it, it will keep on turning. So what there should be? There should be some spring kind of. So this is a spring, okay. It will stop it to turn. More the torque, greater will be the deflection. More the current means greater will be the deflection. Lesser the current, lesser will be the deflection. So this is how it is measuring the current there. Getting it? This is how it is measuring the current. This was your needle. You got torque due to magnetic field. So you are turning. Spring stops you at a particular angle. Where? When both the torques will be equal. Okay. So if I ask you the torque first, let me find what is the torque due to magnetic field. So you say, sir, torque is mb sin theta, m cross b. This is basically mb sin theta. M is number of turns into the current into the area into b sin theta. Now here galvanometer is designed in such a way, this theta is very, very small, approaching, this theta is approaching 90, not very small. This galvanometer is designed in such a way that this theta approaches 90. So sin theta approaches 1. Sin theta approaches 1. Okay. So I can write this as NIAB. This becomes my torque. Okay. Now this is the torque due to magnetic field. Spring is there. This coil is trying to turn. This spring is having some torsional constant. Okay. Some torsional constant, and the torque due to that spring, that torque due to spring is mentioned as the torsional constant of the spring into the angle turned by the spring. What is this? C? This is the torsional constant of spring. As we had spring constant K, that was force constant of the spring. Force was equal to spring, that force constant into the elongation in the spring. Similarly, this is the torsional constant. The torque is equal to the torsional constant into the angle theta. So the torque is C theta. Where this needle will stop? Where it will stop? When both the torques will become equal. So C theta is equals to NIAB. There it stops. This is the condition to stop. So from here I can measure the deflection also. How much deflection is there in the galvanometer? Okay, and accordingly I can mark the values here. Okay, so I will see, okay, when the current is 10 milliampere, the deflection is this much. So I will mark this point as 10 milliampere. Sorry, 0.1 milliampere. When the current is 0.1 milliampere, I got the deflection. So I will mark this as 0.1 milliampere. So similarly, I will mark other point as well on this. This is how the meter will be made. The readings will be made there. Okay, now current sensitivity and voltage sensitivity. We got the formula. What is that? C theta is equals to NIAB. C theta is equals to NIAB. The deviation per unit current theta by I, that comes out to be NAB by C. This we call as the current sensitivity. This we call as the current sensitivity. Let me write it. This is my current sensitivity. The deviation per unit current, that we call as the current sensitivity. If deviation was theta per unit current by I, that becomes NAB by C. Sometimes we use K in place of this C. So don't confuse, it's the same thing. Okay, this becomes my current sensitivity. If I ask you what will be the voltage sensitivity, you will say, sir, theta per unit volt. Okay, so let us write that also. So voltage sensitivity if I write, you will say that is theta per unit voltage. So how to make that? By dividing with R, because V is equals to IR. So divide this with R. So this will become NAB by CR. Okay. This becomes my voltage sensitivity. Now, if let us take I increase the number of turns to twice, current sensitivity will become twice. Yes, that will become twice. What about voltage sensitivity? You made the number of turns twice, resistance will also become twice, the voltage sensitivity will remain the same. Okay, so by increasing the number of turns, you are able to improve the current sensitivity but not the voltage sensitivity. That one thing we can see from here, and that you need to keep in your mind. Okay, again I am repeating the same thing if you lost the point. If I increase n to 2n, the current sensitivity will become twice. N to 2n, here it will become 2 times, but resistance will also become 2 times. So voltage sensitivity will remain the same. Okay, that point I was saying. Now coming to questions. The current sensitivity of moving coil galvanometer is increased by 25%. The increase is achieved only by changing the number of turns of the coil and area of cross section of the wire, keeping resistance of the galvanometer coil constant. The percentage change in voltage sensitivity will be, okay, write it properly. So when I say current sensitivity, what was that? Theta by I, and what was that? NAB by C. The same formula. When I am saying the voltage sensitivity, theta by V, that is NAB by C into R. Here initially was saying they increased this by 25%, this is increased by 25%, and this is done by keeping the resistance to be same, only they increased the number of turns and the area, only they changed this. Okay, they changed this but they kept resistance constant, that they are clearly saying. So how much this will change? Now resistance is constant na, that is not changing, only this is increasing, these two is increasing, so it will also be increased by 25%. Okay, so the percentage change in voltage sensitivity will also be 25%, will also be 25%. Is this clear? Okay. Next question. A current of 200 microampere deflects the coil of a moving coil galvanometer through 60 degree. The current causes deflection through pi by 10 radian S. Now it is the same galvanometer. If it is the same galvanometer, then my current sensitivity will remain the same. Current sensitivity means theta by I, this is constant. So I will say theta 1 by I1 is equals to theta 2 by I2. Okay, what is theta 1? 60 degree pi by 6. What is I1? 200 microampere. What is theta 2? The current to cause deflection of pi by 10. Pi by 10 is theta 2, pi by 10. And I2 I need to find. Pi got cancelled. So from here I can say I2 comes out to be, this is 200 divided by 60, isn't it? No, this is 200 into 6 divided by 10, this much microampere. Properly I mentioned it, 200 into 6 divided by 10, yes. So this comes out to be 120 microampere. 120 microampere B. Okay, 120 microampere. I hope you are solving all the questions till now with me, and if you missed some of the questions, make sure you solve it solve them separately, and make sure you download, get the DPPs and the class notes from the link that is given below. Okay, when you click that link, you'll go to the app. There you can access the notes and the DPPs. So DPPs are a good collection of questions for you to practice on this particular chapter. Other than this, now till now you have practiced question with me. So question with me means you are taking help from me. I was saying something, you got the point. Okay, this is correct, I can write like this. But when you will be solving, you'll get some doubts. And when you'll have doubts, come back, comment on this video, we'll get back to you. Okay, so thank you all. Have a nice day.